Good morning. Welcome everybody to this morning section of the second day of Pepe's Birthday Congress. It's a pleasure to present Professor Jorge Vittorio. He's going to talk on the reduction of foliations to positive characteristic. Thank you.
Okay. Thank you very much for the invitation and the opportunity to give a talk here. It's a pleasure and a real honor to participate in this event celebrating the 70th birthday of Pepe Seade. I could spend half of the fifth perception. I could spend half of my talk enumerating the many qualities of Pepe, but I would like just to express one of my greatest admiration for him is for his gentile leadership. So it's an honor, and happy birthday, Pepe. So this talk will be, there will be no great theorem, there will be no main result. It's just trying to share some ideas that I've been trying to pursue in the last 20 years or so. So do not hesitate to ask questions, or I just try to convey some ideas. And it's about one of my favorite objects, the ones that I spend most of my career thinking of. It's about codimension 1 holomorphic foliations. So that's the main character. So F, codimension 1 holomorphic foliation on a projective manifold. So to say that something is holomorphic on a projective manifold gives you some finiteness condition, essentially that your object is defined by finitely many equations involving finitely many coefficients, and you can always collect these finitely many coefficients into a finitely generated Z algebra. So attached to a foliation, once you choose equations to define it, you have a finitely generated Z algebra generated by all coefficients of all the equations appearing in the one forms defining your object. And the point of this talk is to try to explain how much of the geometry, how much geometry you can extract from the simple idea of reducing everything inside modulo a maximal prime ideal. Of course, this seems like, so how much, I'm just writing what I said before, how much of the geometry of X can be extracted from the reduction of its equation modulo a prime ideal, a maximal prime ideal of R. Of F, thank you. And the point is that we can extract a lot of things. So let me start the very simple observation. Why should we care? Why should we try to reduce a a foliation modulo prime ideal, because you obtain then an object defined over a finite field, defined in positive characteristic. And in positive characteristic, you have operations that you do not have in characteristic 0. So the key thing is that if I have a field of characteristic P greater than 0, and I have V, a vector field, defined on a variety over this field, then V to the power P is still a vector field. This is just because when you compute V to the power P in a product of two functions is just the sum . Yes, exactly. I'm seeing P as a derivation, and I'm just writing down Leibniz rule, iterated Leibniz rule, and you get then something like this. Okay, so you have this kind of interesting operation. Of course, we can iterate derivations in characteristic 0, but what we obtain is a higher order differential operator. It's no longer a first order differential operator, but in characteristic P, this is what happens. So already, so let's assume now that X, the first remark, let's assume that X is a surface over a positive characteristic field, and let's assume that we have a foliation, F, and this foliation is just, if you want formally, what I'm thinking is of rank 1 subsheaf of the tangent sheaf of X, and if we denote by, so since we are in rank 1, so dimension 1, foliation. So I can just denote omega f by the dual of this guy, and it's a line bundle. Both TF and omega f are line bundles. And from this operation, I can do the following. If I have VP, V, if locally, TF is generated by a certain vector field V, I can just produce a divisor. V to the power P is not something intrinsically attached to the foliation because the generator is not unique. You might multiply it by a unity, and you take P powers, things is not all linear. But still, if I try to understand the ambiguity in this operation, you see that what you get is something like U, P, VP, plus a certain expression times V. So nevertheless, this will define, or at least the zero set of this thing will define a divisor which is intrinsically attached to the foliation. Unless V wedge VP is identically 0. So already, so in positive characteristic dimension 2, we have a certain dichotomy. We have two kinds of foliations. The ones for which VF delta F V wedge VP is identically 0, or we have a delta F indifference.
What's the precise
I'm just taking the sheaf of vector fields tangent to the foliation. So for me, a foliation is just a singular foliation. So for me, a foliation is just a rank 1 subsheaf of Tx. And I kind of avoid apparent singularities. I don't want to have torsion in the co-kernel. Which comment? So you have this thing. So it's an equivalence class of vector fields. So we have a bunch of vector fields, all of them differing by multiplication by a unit locally. And using this operation of taking beef powers, I can produce to each generator a VP. VP does not have intrinsic meaning because of this expression. There is some certain ambiguity. But when I take the wedge product with V, these terms disappears, and I have something intrinsically attached to the foliation, a divisor, a curve, right? So this curve is capturing something of the foliation.
What's the takeaway? I don't understand the logic, but what's the takeaway?
The takeaway is that you have two kinds of foliations. The ones that for which this thing is identically 0, and the ones for which I have a curve intrinsically attached to it.
You have what?
A curve, a divisor, an effective divisor. The curve is given by locus of V wedge VP. Sorry?
The foliation becomes a curve.
No, the foliation gives you a curve. Something that we don't see in characteristic 0 unless you give extra information. Okay? And the point is this. So this case is what are called P-closed foliations. So we are in characteristic P. And this is the analog of algebraically integrable foliation. In this case, so this happens if and only if there exists a rational function which is not a constant of derivation. In characteristic P, if you have a function and take the pth power, the differential is 0. So I'm saying that I have a function like this, and such that V wedge F is identically 0. So these are the algebraically integrable foliations. The leaves are algebraic, whatever the leaves are. And in this case, so I can port contains all invariant algebraic curves. And moreover, the irreducible components of the support, which are not pth powers, which do not appear with multiplicity divisible by p, are invariant. So somehow, problem that is completely wide and impossible to solve in characteristic 0. I give you a vector field, a polynomial vector field if you want. Compute the invariant algebraic curves. It's impossible in characteristic 0, not impossible, but it's unknown if it's decidable or not in characteristic 0. In characteristic P becomes a very simple algebraic computation. Okay?
What's the question in characteristic 0?
So I give you a vector field. So this is a problem that was studied in the late 19th century, beginning of 20th century. You want to know if there is an algorithm that says, yes, here are this thing is algebraically integrable, or no, there is no algebraic first integral. And you can also ask for invariant algebraic curves. Okay, so in characteristic P, this is very easy. In characteristic 0, it's still unknown up to date. But you have this thing. And you can ask, this info back to characteristic 0. So here's the thing. You start with something, just think that you have a vector field defined over Z. And then you start to reduce mod P, and you do this thing for every single P. And you try to compute, see if this is 0, or if not, you compute this thing. You get invariant algebraic curves in characteristic P. you want to know if I can just lift. So if there is algebraic invariant curve in every p, probably you would have in characteristic 0, but the problem is that you cannot do this. It's hard. Hard to do this.
Does it mean that in characteristic 0 you have an line curve which is kind to the foliation?
You're going to see
Modulo p is containing the support of
for almost every p this will be true. But not, perhaps there will be some strange p's. Your curves might have many coefficients divisible by p and might mess things up. But for almost all p's, this will happen. Okay? So why this is hard? So the first case, so there is this conjecture, if you want, which in the case of linear differential equations is due to Grothendieck cats. And in the case of foliations is due to Ekedal Taylor. That says essentially the following: if F now is from characteristic 0, we do that thing and assume that is P closed for almost every P, meaning except for a finite number of primes, then F in characteristic 0 is algebraically integrable. P closes the first. So you have first integrals in characteristic P. You might wonder if I can lift it back to characteristic 0. Okay, so this is wide open. We know in very few cases. So perhaps the most important case is the case of linear differential equations associated to families of varieties, meaning Gauss-Mannis equations. And this is the theorem of Katz from the 70s, I think. And there are also this very nice result by Jean-Benoit Bost that says that this is true if your leaf is to be closed and you have a leaf that is Liouvillean. Liouvillean in the sense of potential theory, meaning every bounded harmonic or subharmonic, pluri-subharmonic functions is constant. But in general, it's wide open. And this thing already shows, if you look at the complement, there is no real conjecture there. But the point is that it already explains the difficulty of the problems. That the point is that this delta F, right, is given by the vanishing of this thing. But this guy is a section of X wedge 2 Tx tensor omega F tensor omega F to the power P. So if you think of this line bundle as essentially the degree of the function, which is not very far from 2 when you are dealing with relations on P2 coming from polynomial vector fields of a certain degree. You are saying that this divisor, this curve, will have degree which grows with P. So you always have these invariant algebraic curves in positive characteristic, and but you cannot lift it because the degree is not bounded. There is this general principle, right? You start something in characteristic 0, your object, your favorite object. You do this procedure of reducing modulo prime. If for a Zariski dense set of primes you have objects with have bounded degree, you can lift it back to characteristic 0. But the problem is that here the objects are not bounded. This family of divisors that I'm obtaining by varying P is not a bounded family. Okay?
You're still in dimension 2?
I'm still in dimension 2. So this is useless.
So lambda P, 0 P?
Sorry?
0 2 or 0 P?
Stereo P.
Lambda
Lambda 2, this is the effect. This is a 2 vector, right? So this part is fixed, good. But this part is not. And this gives problem to lift your objects. So this is where I were 20 years ago. And it seemed that was just a curiosity, right? You do these computations, you can find curves, you can amuse yourself by playing with them, but seems to be just a curiosity. But then, some other remark that we did really early was the following. So, what is this VP, right? I don't know what it is. I cannot draw vector fields in positive characteristic. But if I use my intuition from characteristic 0, I see that it has some remarkable properties. The point is that you can convince yourself quite easily that algebraically VP commutes with V. I don't know why it is, but I know that it commutes. But now I have a foliation and one generator of it, a vector field, and back to characteristic 0. And I have a vector field that commutes with it. The flow of this other vector field is an infinitesimal symmetry. And we know that sincerely that when we have an infinitesimal symmetry, we can reduce your equation one-dimensional, essentially. It's not exactly true. There is a problem of local determinacy, etc., etc. But the algebraic part of this discourse tells you the following. If I take omega, a one-form defining f, is that kernel of omega is TF, at least locally, then omega divided by omega v to the power p, as soon as this thing is non-zero, which is essentially the same thing as saying that v wedge vp is different from 0, this is closed. So we have this strange situation in positive characteristic. Give me any one form in dimension 2. Then it is proportional to a closed one form. Something that's far from true in characteristic 0. But well, very good. We have this integrability thing. In characteristic 0, when you find a closed rational one form defining a foliation, you give a party, right? Because it's you say a lot, you're saying a lot. You're really restricting your foliation. But again, the same problem we have here. Positive characteristic, the poles, I cannot lift back to characteristic 0 because the poles of this one form will have very large degree. The degree will grow when I vary the characteristic. Anyway, we have this. So this is in dimension 2. So all seems to be very ineffective in dimension 2, just a curiosity. But let's stick to codimension 1, but let's move to higher dimensions. So now assume that dimension of x is greater than 2. And I can still play the same thing. The difference, of course, we are talking about codimension 1 foliation. My tangent sheaf, the sheaf of vector fields tangent to the foliation is no longer rank 1. I have plenty. But I can always still do the same game. I can take 1, take the p power. If it's tangent, okay, don't do nothing. But if it's not tangent to the foliation, I have a closed rational 1 form defining my foliation. But in positive characteristic, for closed rational 1 forms, we still have another operation that kind of a relative of this p power. So this is the Cartier operation. So this is something that Cartier introduced in his PhD thesis. It's very, very old. And it's essentially the following. So point is that in positive characteristic, we have many more closed 1 forms than we have in characteristic 0. For instance, over A1, the most simply connected thing that you can imagine, you have that xp minus 1 dx is closed. But what's the primitive of this thing? The primitive, as we all know, should be something xp divided by p. And we cannot divide by p in positive characteristics, so this thing does not work. It does not live in our setting. But what Cartier introduced is the following thing. There is a morphism, or map, C, from closed rational one forms, modulo, exact rational one forms, to rational one forms. And moreover, this thing is an isomorphism of vector spaces. I'm being a little bit informal. I will have to twist Frobenius to get linearity, but I don't care. It's just, if you think as a set, it's isomorphic. And essentially the operation, the inverse operation would be something that associates dx, something like this. So this is the Cartier inverse. Okay? And this is a very nice operation, very useful to do lots of things in positive characteristic. And for us, it is linear, but the problem is that there is, you have to twist, because it not takes f to f. It takes fp to f. So it will be linear if I do the push forward of this thing by the absolute Frobenius. But this is just a detail. It's just okay, so we have this operation, and there is this very nice formula. This is a Cartier formula. If you take omega, a closed rational one form, a Cartier operator, and raise to the fifth power, then this thing is the same thing as I will do the interior product of V with Cp. It's just the contraction of this one form with V. So it will be the same thing as contracting the fifth power of V with omega. Right? So this is a function. I have here a function minus V to the power P minus 1, seen as a differential operator, applied to EV omega. IV is just the contraction. I could write this as C omega V. Okay? C omega V to the power P. Very interesting. And why why do I care about it? Well, because now I start with a foliation F in positive characteristic P. I can associate, let's call this closed rational one form, theta. It's a closed rational one form. I can consider its Cartier operator and look at the of theta, which is just Tf, intersect with kernel of C theta. This will produce a subsheaf of Tf of codimension 1 inside Tf. So somehow magically, I'm producing a subsheaf, a codimension 2 foliation or codimension 2 distribution contained in my foliation. Right? And the nice thing is that the degree of this, so I have, so this implies there exists D, a codimension 2 distribution tangent to F. So of course, here we are in characteristic K, P positive. And notice that we are producing this codimension 2 distribution only assuming that your foliation is not P closed. After that, there is no choice involved. It's completely canonical. So I give a codimension 1 foliation, pow, codimension 2 distribution on it. Sorry?
Why does it have that dimension?
Because this is a one form. So I'm just intersecting the kernel of two one forms. If they were equal, this would mean that it's P closed. So it's not equal, so it must have codimension 2 equations. Very good. Now, the point in the nice thing is that whatever that means is that the degree of D is bounded by a function, by a constant, that does not depend on P. So this is something that I can lift. This distribution can be lifted to characteristic 0 if my foliation comes from characteristic 0. And even more, we have results theorem. This is joined with a student of mine, a former student of mine, Mendelssohn, that says the following: if F lifts to ring of width vectors of K, the second ring of width vectors of K, then D is integrable, is a foliation. It's involutive. In positive characteristic, regardless of coming from characteristic 0 or not, this D does not need to be involutive, but when it comes from characteristic 0, this is a little bit more general than that, or it's more general than that. When it comes from characteristic 0, it's involutive. It's a foliation.
This omega defines the foliation involves the integrability condition.
Yeah, it's a foliation. Foliation for me is something, is a subsheaf which is involutive. It's involutive. Then I produce some other subsheaf which is not necessarily involutive. But if my foliation positive characteristic comes from characteristic 0, it is involutive. Okay? So there is a question, so we can lift. So this thing that we are seeing, this shadow that we are seeing in characteristic P, has some counterpart in characteristic 0, at least it has some counterpart in characteristic 0, but the point is that this counterpart is not necessarily unique. Right? I don't have a canonically defined foliation D in characteristic 0. This foliation may vary from P to P. Let me give you one example just to see that I'm not completely crazy. A simple example. So let's take foliation defined by the simplest kind of form which is not integrable, just a closed meromorphic one form. Closed logarithmic one form. Let's say that I'm on Pn, these are projective coordinates, and so for this to be a global one form, to descend, I need to add something like this. I'm already giving the closed rational one form define the foliation. And in this situation, for logarithmic one forms, it's very simple to compute the Cartier operator. The Cartier operator in this case is just of lambda I. This is always like that for logarithmic one forms. For applying this Cartier operator to logarithmic forms is just taking the pth root of the residues. And here you see that this, of course, I will be able to lift this thing. I will be able to find complex numbers whose reduction mod p will be this roots of lambda I, no matter which lambda I take. But this will vary from p to p. The choice even is not unique, and I have plenty of lifts of this codimension 2 foliation, 2 characteristic 0. Okay? Any question? So just to give a hint of what we can prove, for what kind of things this is useful, let me just explain how we can use this thing to prove an old result. So a result by Calvo-Andrade. Calvo-Andrade theorem says the following. If I take a generic logarithmic foliation, I take a generic foliation on some variety of dimension, at least 3 defined by a logarithmic one form. Here generic means that these polar divisors, the irreducible common of the polar divisor are sufficiently ample and that the residues are sufficiently general. So Calvo-Andrade says that logarithmic foliations or generic logarithmic foliations are stable. Right? So when you deform a foliation like that, you do a very small deformation, it will still be, it will not be topologically conjugated, it will not be the same foliation, but it still be logarithmic. It will still be defined by a logarithmic one form. And the proof of omega is a beautiful, very, very interesting. It involves studying the holonomy of the foliation, looking at the Kubka set. It's intricate, but very geometric, very beautiful. And here I can offer you also a very geometric proof, but kind of strange. It's, I will not say that's easier, but the point here is that these foliations, for logarithmic foliations, are essentially characterized. So this is with quotes. Logarithmic foliations are essentially characterized by the fact that, or generic, let's say, delta f is reduced and of minimal degree, whatever that means. So you compute, you try to understand this somehow from this point of view. These foliations are the simplest ones. And delta f, yeah, thank you. I was kind of cheating a bit. The point is to have this map, right? We have the tangent sheaf of the foliation. I can take a vector field here, and I can map to VP. And this is a morphism of sheaves, but it's a mess, because this operation is not linear. When I write down V plus W and raise to the power P, you get V to the power P, W to the power P, plus a Lie polynomial on V and P. And the Lie polynomial is very large. If you open Lie algebra's book of Jacobson, for P equal 5, you have a page of a formula to express this. But anyway, you lose linear additivity. But if you do that, because we are talking about Lie polynomials, you get something which is additive. It's morphisms of additive groups. But it's not linear. You want to do geometry. To make it linear, you pull back this thing by Frobenius, and you're good. So you have a morphism of sheaves. And my assumption is that this thing has generic rank 1, because F has codimension 1. And so the core support of the image is something, and the delta F is the part of codimension 1. It's the codimension 1 part where this morphism is not surjective. Locally will be defined by omega VP. So delta F will be something that locally is like that. So this is the normal, yeah. Outside the singularity of is not the normal. I like to call the normal the bit bidual of this, but yeah, you can call.
Also
Baumbot calls it the normal sheave. But then you have this divisor, and this divisor will have the minimal degree possible. The degree is not completely determined by the degree of f. There is a game here between the degree of delta f, which is the degree of the image, and the degree of the kernel. So when the degree here raises, things become more wild and cannot lift. You get something inside TF which is smaller. And you can lift and you get more information. So you have this game that you can play. And essentially, you see that these properties are stable under deformation by just coating different parts of Hartshorne or GA or whatever. Okay? So this is one possible application, but this is just proving something that we already knew that's true. That's the best kind of proof, right? You feel confident that you're going to arrive somewhere. But here we can prove something much more general. Because it does not really look at the, generic is different. So another application that we got, but now for, in a similar vein. So here we are exploring the case of delta f, the smallest degree possible, but when the delta f has large degree possible, we also have a result. So this is also a theorem with Manson, which says that if I start with F or G, a generic foliation on P1 times P1, I take pi from Pn to P1 times P1 linear projection. It's just the product of two linear projections. I'm saying that this is defined by linear forms. And we take f equal to pi star of g. Then f is, let's call it's stable. In the sense, again, the same sense there. It's not that f is stable in the usual topological sense, but it's kind of structurally stable. If I perturb f, I get a very same description. When I perturb f, I will be able to perturb g and perturb that. And here is the case where delta f is almost maximal. And the strategy is essentially that kernel of this intersection of the foliations of f and d is given the fibers of this map. And you perturb, and you can see that it still be of the same kind, and you can conclude. And I think it's a good time to stop, and thank you for the attention.
Are there any questions?
This is one of this was in this paper by Ekedal, Scheffer, Baron, Taylor. They conjecture these things that are P-closed, blah, blah, blah. Now, P-closed implies algebraically integrable. And one important case was the case of abelian variety. So it's saying that if I just take a Lie subalgebra of the, of algebra of holomorphic vector fields on abelian variety and assume that P closed for almost P means that it's the tangent space of some abelian subvariety. And this is one of the cases that is proved by Boss, because in this case, obviously, the leaves are the prototype of Liouvillean stuff. So this is the motivating case of Boss' theorem. But in this case, if we do that, in the case that's not P closed, is the case where delta F, it will be transversal. It will be completely transversal. But yeah, you can. We do not go to the formal neighborhood of the point. We are just reducing mod P and doing everything there. We haven't did p-adic stuff yet. and I'm not sure I'll be able to do it. But I have a question. So why do you care about this, right? So for me, the most important conjecture, the most important question about codimensional foliations is this alternative. We have very few examples of codimensional foliations on projective manifolds. Every single example that we have are either of one of the two cases. Either it's just the pullback from something on a surface. Foliations on surface are easy, there is no integrability condition. You just take a rational vector field, a rational one form, voila, you have a foliation. And these are dynamically intricate. They are very complicated. We know that it's very wild. But besides that, all foliations that we are aware of is foliations which are transversely projective. So if it's not like this, the foliation is transversely projective on a Zariski open on the complement of hypersurface with singularities on the hypersurface, doesn't matter, but it's always like that. We have this dichotomy. And it would be, if we believe in this conjecture, depending on the day of the week, I believe, it would be better to find a way to, in case that it comes from a surface, to recognize the fibers of the rational map, right? And in the case that it comes from a surface, that's what we are doing. This codimension 2 foliation, in the case it's a pullback, are the foliations given by the fiber of this rational map. And so this is perhaps an approach to investigate this conjecture.
Any other question, please?
One question. Yes, for the case of foliation of dimension 2, assume that you have a foliation with a rational first
Uh-huh.
Can you get extra information about the period device or how they grow with period? What of this rational did you explain for this?
Not so far. I don't know how to do that. And I have to say that I'm really, how to say, overwhelmed by this Grothendieck, Katz, Ekedal, Scheffer-Parent. So I prefer to work on the complement. So these are essentially, there are a lot of work on that, but yeah, no, it's very, very complicated. For instance, one useful tool to understand the first integrals in characteristic 0, there are plenty of questions, but one useful tool to understand first integrals of foliation characteristic 0 is a classical theorem of Halphen, for instance. If I have a rational map with generic fiber reducible, then there will be at most 3 multiple fibers. I don't know if this is true in characteristic P. And all the kind of computation that you do, it's much more trickier. And at the beginning I played a bit, but I couldn't see nothing. I think it's hard.
Another question? Well, let's thank the speaker again, please. And we come back at 10:30.
grabando? Sí. Apago.
Our second talk today, this morning, is by Luis Núñez Betancourt, and he's going to talk about the RAM homology of D modules. Thank you, Luis.
Thank you. First, I want to start thanking the organizer for giving me the opportunity to speak today. It's very nice to be in a conference in honor of Pepe. I met Pepe relatively recently, in 2015 in Brazil, in a conference on singularities. However, his impact on my career was done long before. When I was in high school, I didn't know what to study. I was debating between different things. So I talked to several friends who participate in the math Olympiads, and after talking to them, I decided that I wanted to study math. So even though I didn't participate in a contest, the project that Pepe started changed my life. So thank you, Pepe. Okay, so today I'm going to talk about the RAM homology of D modules. This is a joint work with José Álvarez Montaner from Universidad Técnica de Cataluña and Jack Jeffries at Nebraska. Sorry. So I'm going to start with some notation. Okay. Okay. Pardon me? No, I'm going to do all of that. Yeah. Yes. So for this starting, R is going to be polynomial ring in variables. Just that for the moment. And definition, the Weyl algebra over defined by, so I'm going to do like this, but a lot of times I'm going to forget about the subscript, and it's just going to be D. So this is R over C. And then here we have that the R linear homomorphisms from R to R is just isomorphic to R. So every map from R to R is defined for where you send one. Okay, so I'm going to use a little bit of notation and just write that they were equal. So because every map that is linear has to be C-linear. So this is going to be R, thinking of this here. And then I'm going to add other linear maps, C-linear maps, from R to R, which are just the derivatives. So I'm looking at the smaller ring, subring of the linear transformation from R to R that contains multiplications by every element in R and the partial derivatives. And this is going to be my Weyl algebra that I'm going to call D. Okay? Okay. So,
That's not a question, because I don't understand. I don't have a question.
well, I can mention a little bit more. So if I have a map from R to R that is R linear, this has to be C linear, no? Because C is contained in R. So it's C linear. And then this map is just, every map here has to have the form multiplication by an F. So here is when I use notation, and then I write F instead of phi of F. And then if I look at the subring, D is going to be the subring of all the C-linear maps, which is, this is going to be the one that is the smallest subring that contains R. So it's that contains R, or all these maps, and the derivatives. No, derivatives is as an operation. Every derivative is some. Yeah, from R to R. R is the ring, is the polynomial ring. Yeah, and I am identifying that with all the maps from R to R, which are defined. Yeah, but where you send the one. So This is going to be my Euler algebra. No, this is D. It's just like, yeah. Sorry, yeah, that's something hard to change after a life of writing D, like, yeah, like I know. Okay, so I'm gonna focus on left modules over this ring. This is a D module, a left module over this ring. Let me give examples. So the first one is R is D module by evaluation, no? Because at the end of the day, these are mapped from R to R. So if I have a map here and an element here, the action is just going to be to evaluate. And also, if I take the localization, which is just having R and adding the fraction 1 over F, this is also a left module. It's a D module via the quotient rule. So if we want to define an action of D here, it's enough to define it in the derivatives. But we know that from like high school. So di of R over F to the alpha. This is F alpha times the derivative of R minus R times the derivative of F alpha, which is alpha F alpha minus 1, derivative of F over F to the 2 alpha. So, and I'm not going to define it, but for those who are familiar with local cohomology or with shift cohomology, so because these are D modules, any local cohomology module is a left DR module. I'm not going to define that. This is just like a comment for those who are familiar with this. And actually, this is, you know, I am an algebraist, and this is what got me working, well, commutative algebraist, and this is what got me working on a non-commutative ring. Yeah. Yeah, I'm trying to push as much as I can. Okay, I can try the other brand. See if that works. Okay. 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 So a particular property of these modules is what's called the Bernstein inequality. Better? Okay, I use this then. So if we take a D module, then its dimension, which is, I'm not going to define it, but this is the dimension. There are different ways to define dimension over a non-commutative ring. But you know, intuitively makes sense. So the dimension of a module is going to be bounded by D, which is the number of variables, even though this is a ring, you know, over the ring of differential operators, and between 2D. And the 2D comes because, you know, we know that this has dimension D, and this somehow the derivatives are what makes the dimension double. Like this is somehow variable again. So the key part or the unexpected thing here is that there is a bound, a lower bound for the dimension that is not 0. And the modules that satisfy this bound, that what this is equality, are called holonomic D-modules. So a D-module M is holonomic if its dimension, well, if M is equal to 0, so here you should say different than 0, or its dimension is equal to the minimum. It has the smallest possible dimension. And surprisingly, every holonomic D-module has finite length in the category of D-modules. So let me go back to the examples that I have over here. So all these three examples are holonomic. And what is a bit like it's very useful, especially in commutative algebra, is that this module over R is infinitely generated. And the same with local cohomology. So they are difficult to control. If you want to check properties, it's hard to manage. We don't have. What's the length of a module? Well, we define a simple D module as that doesn't have proper submodules. Or the only submodules are the trivial ones, 0 and the whole thing. So the has finite length is that it has like a flag of modules or like a filtration ascending, which is finite, and every quotient is simple. That doesn't have, the only submodules that it has are the trivial ones, like the whole thing and the 0. So if we were working over a field, that will be the equivalent of having finite dimension. But this is a non-commutative ring, so it's a little bit more subtle, the notion. But thanks to that, this means, like, for instance, yeah, actually, the proof and the definition of dimension is using the associated gradient. Yeah. But for instance, something that a D module has finite length implies that it's finally generated. It's actually much more stronger, the finally generated. But here, if we're working only over R, infinitely generated, we make the ring bigger, becomes pretty small, and it can be controlled. And many properties about local cohomology over R have been proven using its properties over D. Yeah.
Also the length?
Mm-hmm. Yeah, the length. Yeah. Okay, so let me give the first ingredient of the title. Is I guess. As I mentioned, I come from the commutative algebra world, and to me, what matters is that algebra, because I come from a different side. Okay, definition. So let M be a D module. It's the RAM cohomology is better, no? Is the cohomology of the following complex. So, okay, we're going to build the RAM complex using this. So we have M. And then M tensor omega 1 of R, which is I'm building that complex, the RAM complex. So the map from here to here, I have V. And what I do is trying to mimic the RAM complex using the derivatives that we know how it works here. So this is going to be the sum from J equals to 1 to D, the derivative of D. So because this action makes sense in the D model, and then we do tensor D of x1, of x, sorry, xi. And then we extend as we usually do. So the cohomology of this complex is the RAM cohomology of the D model. And a theorem in this direction is by Van den Essen that says the following. Pardon me? Let me do, which I think is a bit more meaningful, of R, which is holonomic. Okay. And I'm going to do it just in one variable to make something super clear. Okay, so, pardon me? The theorem, okay, finish the theorem. So let M be a holonomic D module. Then, let me go right here. If I take the RAM cohomology of this holonomic D model, this is going to be a complex vector. It has finite dimension. It's something that we know for holonomic. And let me show that in R. So if this equals 1, no. It's quite subtle because here we're working with something super big, X model, well, X groups in this case over a non-commutative ring. So this is not, well, no, it's not X, it's a cohomology. So now what we have to do is, let me give an idea of the proof, and then I'm going to mention. So, and then give the example. So a key idea of the proof is the following. So if I have R as a D model, I want to build its projective resolution over D. So here we have a symmetric map that sends every operator to delta applied to 1. So the kernel of this map are going to be all the derivatives, because all the derivatives kill 1. So the kernel is D, R, this left ideal. And then what hits this, you want to build this. So we do this. I want to continue this. And for those who are familiar with the Koszul complex, it's kind of what we built, but for this operator. Until yeah. And so what Van den Essen observed is that if I take this complex, yeah, it's the derivatives. The left ideal generated by the derivatives, because every derivative kills the one. Yeah. Well, not dual, because I mean we're in a non-commutative ring, so we don't have Koszul complexities. This has like a different names than very, very specific properties. No, we need that these things kind of commute, and I mean. But what people observe is that if we look at the RAM cohomology of a module, this is going to be, if I call this complex F bullet, then it's the same as the hom of dr of this complex with M, which is the same as the X, which is the same as the Xi of R with respect to M. So the Riemann cohomology is given by an X group, which is no longer a D model because this is not commutative, but it's a vector space. And if we, coming back to your example, I mean, we can do it directly. So we have R. Let me assume this equal 1. So we have only one variable. And then it goes to R tensor R1C, and then it finishes. The map from here to here is we take a map, a polynomial, and then goes to the sum of the, well, there is only one variable, so it's the derivative with respect to that variable of f tensor dx. So the kernel of this map is going to be all the constant functions. So this is, the cohomology is going to be C. And then if we want to see what's the kernel here, it's going to be given by the image of everything that's a derivative. But everything is a derivative. We don't have to integrate. So this is going to be surjective. So the first cohomology is C. The second cohomology is 0. And this gives you an idea how to go for our variables. So let me try. I want to do this to extend this to other algebras. So what happens if R is not a polynomial ring, but a quotient? So then there is a definition of differential operators, or an analog of the Weyl algebra, but it's much more complicated. So the differential, here I'm changing to K because sometimes I want to go over the complex number, sometimes over characteristic P. Differential K-linear operators are defined inductively as, so the order 0 are the R linear operators, the same that we know that are isomorphic to R. And then for others, I look at every K-linear operator, sorry, K-linear transformation, to the commutator of this with the things of order 0, which are given by multiplication by an element. This decreases the order. So this is like a higher version of the Leibniz rule. And something that happens is, well, the ring of differential operators is just a union of all these. And this is not always generated by derivatives. There may be a lot more things happening. Actually, there is a conjecture of Nakai that this ring is generated by derivatives if and only if the ring is smooth. So we have singularities. We expect that this is not generated by derivatives, that we have other operators. So in this case, we have a different notion of, there are some singular rings when we have notion of holonomicity, or holonomic models. So we have a notion of holonomic models. If first R is, we take a polynomial ring that which a finite group is acting, and we take the ring of invariance with this group finite. So this is a singular ring, but it's not too bad. We know that it has, for instance, rational singularities and other properties. There is also, what do we want to do this, but in prime characteristic, or for instance, if R is something is a toric algebra. Sorry? 1 or 2, yeah. Yeah, we're just changing the characteristic, but this means, because even in this case, just because we change the characteristic, the derivatives behave weird. It's like what we heard in Jorge's talk, no? There are some things in which P is acting. No? For instance, every derivative kills x to the p. Okay? So in these two cases, we have a notion of holonomic D-modules. So that means we have some sort of Bernstein inequality. This was a result by Alvarez, Montaner, Hernandez, Jeffries, myself, Teixeira, and Witt. And this is by Babula and Libesnik in different works. So the theorem.
Wait. So that's basically, you have examples of holonomic D-modules?
Yeah. So when
We have a notion, I mean, are these examples of a notion that
there is a notion, what I mean?
derived from the first part, having a definition?
Yes.
Well, which?
Well, we have a Bernstein inequality. So Bernstein inequality. So there is a lower bound of the dimension. Yeah, there's a available definition because we have a Bernstein inequality that I'm trying to avoid because I'm running out of time.
Take the same definition.
Pardon me?
We're using the definition from before.
Yes, but for a different kind of ring. So now we're adding singularities. Yeah, there are rings in which. Uh-huh.
So that sentence there,
Uh-huh.
we have a notion of holonomic D-module.
Okay.
Doesn't make sense.
For these rings,
No, but look at the sentence. Is that the sentence you mean?
yes, and I want to make it more explicit.
We already
With the-
have a notion of holonomic.
But,
These are examples.
but only on the polynomial ring. And what I'm switching is to quotients. Something where adding singularities.
But the definition of Bernstein's theorem, you take as a definition.
Yeah, well, it's the same definition. Okay, what you have to say is the Bernstein inequality still holds. And the Bernstein inequality still holds even in this singular case.
So holonomic.
Yeah, exactly. Yes, yes.
And these are examples.
These are examples where the Bernstein inequality still works.
These satisfy the Bernstein.
Yes, yes, yes. Okay, so because so we need first you need to be able to build filtration, and then we need the filtration to control the certain rate of growth, and these filtrations do not behave very well sometimes. No, there's something else needed. Anyway, so the theorem that I want to mention is, in the first case, let me call this 1 and 2, we still have the same dimension over C of the x. So now it's hard to define the RAM because we don't have the derivatives, but we know that the RAM is an x model. Let's use that as an analog, and we still have Van Densen result. This is in case 1. This is finite, and theorem. Here something happens. So in case 2, so we know here is over k, or over fp x dr 0, which is just the home of mr. Again, this is finite, and we can describe what it is. And x I dr of m equals r, no, sorry, rm is equal to 0 for I bigger or equal than 2. So the only one that we still need to find what it is, or it is 0 or finite, is x1. But it is like an approach to try to get some analog of the RAM cohomology for singular rings or rings in prime characteristic. For me?
Can it be infinite in dimension one?
It could be. I suspect it's not, but I haven't been able to prove it. We haven't been able to prove it. Well, thank you.
There must be a very close relationship with what people in the formation factorization know for the first one. This is statement about the formation factorization.
Okay. I will ask you more about this.
So we have time for just one question.
It's not a question, it's also
Okay.
just a remark about mutation. When I sent my first paper to Durham, and when Durham sent me the answer, he said he put George Durham, and D is with small d.
Oh, okay.
Not
Okay.
big D.
Okay. Thank you.
And this is a mistake many people do. Durham is written with small d.
Okay. Thank you. Thank you.
One question?
If the idealized homogeneous, then this has some global meaning, not only local meaning. Is there some interpretation of this, the RAM cohomology for this case?
Yeah. I mean, you associate with a variety, the projective variety associated. Then this relates to Lubeznik numbers and connectivity and other things, other well-known invariants. Yeah. Topologically invariant. Let me see.
Well, in which case?
In projective varieties. I don't know if topologic, but algebraic invariants, definitely. Topologic, as I suspect, at least for some subset of this. Yeah.
Okay, but let's take the speaker again. And we continue in 7 minutes.
Hello. Hola, hola. Hola, hola. Hola. No, no se preocupen. Bueno, ¿así? Ah, ¿el micrófono acá?
No, lo amarras con el cable.
Lo amarro con el... ¿Es una soga de arcado? ¿Cómo, cómo?
Que no te vayas a estrangular.
No, no,
Sí, no sé. Quizás me quiere estrangular.
no de ninguna manera.
No, es un chiste argentino.
No perdemos muchísimos teoremas.
Ok.
¿Sí?
Hello, hello.
No, no.
Está para abajo. Quizás lo pongo con esto.
Ajá, más cerca.
Aquí.
Aquí ya te puede servir como un formatito, sube más arriba.
Está hecho. Para la mano derecha esto. Ay, ¿tengo que poner el collar?
Lo importante es que estés cerca de tu garganta.
Hello, hello. No. ¿Sí? ¿Se escucha? Hello, hello. Okay. Yell.
Okay, our next talk is by Professor Moira Chas, and it has a great title. There may be more climb bottles and movie bands than are dreamt of in your mind.
So, hi. Hello. I'm honored and humbled, to be celebrating Pepe's 25th birthday here. And there might be undergrad students. You should come closer, especially the younger people. Don't go so far. No, there's no younger. This is okay. I know, but there are more. I know, of course. No, this is for the young people, but there are more. Far? No, okay, they say far. I mean, what? So, wait, give me one showing the way. Well, it's okay. You'll see the whole thing. Okay, so, oh, good. Yeah. Here, because I want to show things. This is for you. Okay. So, what I'm going to talk about is these are results. None is mine, and none is except one that I don't probably will not have time. 9 is very new, but they are interesting ideas. And I don't know, find myself here in this incredible country with this incredible distance. We're so lucky to just, being able to put our minds and think and understand beautiful things. So, no more further. So, the Möbius band. You know the Möbius band. If you don't, never heard, it's like you start with a rectangle, you're going to twist it, and then you glue it, and this shape, we call it a Möbius band. And this is, this gluing, we do it in our mind, and this is very important to keep in mind. It's a physical, and I like to see physical things, and see that is something that we do in our mind. Well, the first time the Möbius band, this will come later. The first time the Möbius band appeared was not in a paper by Möbius, but listing. Here is the picture, and there's some explanation inside the paper. And later, sorry, now it's revealing. No, wait, here it is. Möbius also published a similar description, which is basically telling what I said, and this is the painting that appeared in his paper. So these two mathematicians, both are German, and they've both been thinking about these objects before. So in notes of both Listing and Möbius, 58 year before the publication, these are the notes of Möbius. make this drawing, and he explains we're going to glue this segment with this segment with a twist. And he also made this wonderful picture. Some of it's blends, some are not, depending on you have even or odd twists. And here is a very interesting, for me at least, piece of story, is that it's quite remarkable that these two mathematicians at the same, more or less, time, they are thinking about this very unusual shape. And it's a conjecture, I learned it from a Pond's book, that he said maybe it was Gauss who thought about it. And one of the clues he gives is that in a paper of Moebius, this surface appears. This surface is the same as this, topologically here. If you cannot see, again, I'm gluing here with no twist, both pairs of opposite ends. And that's a torus. I don't know if you can see. Hard to, see, I'll pass it around. This is a torus with one boundary component. Here I have a boundary. This is a disk, and if I glue it, you get a torus, a little fat here, but so I'll throw it to you and you pass it around. People can see. So, but this is a very remarkable surface again, and it's quite a coincidence that appear in the work of these two mathematicians. Therefore, we suspect, it indicates that maybe was Gauss. Oh, and one more piece of data: Gauss told Moebius that Gauss told Moebius about the surface. This is what Moebius says. So we know that the surface came from Gauss' mind. And of course, feel free to interrupt me and ask me. This is a picture later of the Moebius band, and the interpretation that I couldn't bring because space is finite, math mind is infinite, but my suitcase is not. Here is the first written description of the Klein bottle. This one was done by Klein. And he says, going to paraphrase, grab a tube, and you have to do this. If you do it in your mind can do whatever, so you can just glue things in the obvious way. But, here there are two arrows that have opposite directions, and I want the directions to coincide with the gluing. And you have to make, if you want to make this physically, you have to make the tube pass through itself. Sorry. Oh, here. Classical Moebius band that you probably all saw. Klein bottle thing. That's why I married him. And I marked that he says an idea of this might be formed. He didn't say this is the surface. He says we can grasp the surface this way. I asked ChatGPT because I was trying to make a timeline, and I gave all the years that I wanted. I give it a text, and this is what I got. Sometimes this is the time bottle, which makes sense at all, not even Klein name. But this is a more serious Klein. Now, 1882, Klein in his lectures mentioned this surface, and in a book he published about non-Euclidean geometry in 1928, he mentioned the bottle, and he says, I'm going to call it, he says it in German, Klein tube. Later, there's this fantastic book, Geometry and the Imagination, and here they put the Klein surface, they call it. I'm not going to pronounce German because they're Germans and they might do something bad to me. Later, well, this is a picture that appeared in Seifert and Trefal's book. And then there was a translation from the book of Hilbert van Kossen, Geometry of the Imagination, and they translate Klein surface to Klein bottle. And the words in German are very similar. And now everybody calls it Klein bottle, which I'm going to argue is not a great name, and I'm going to tell you why and a little later. But now even the Germans call it Klein bottle. I think it's always a bottle. So here is a story. Here is another picture. My boy. This. And what about this? I don't know if you can see this. I don't want to block. So if you follow this, here we have a tube. Now the tube goes here inside, and it turns in, maybe I'll follow it from here. You go inside, the tube turns, and then comes out, and it was glued to itself. So this is a tube that in some way I glue the two ends. What is it? It's not, huh? It is a Klein bottle. And we could check how can you check that? Well, we have to check. It doesn't look like the standard Klein bottle.
This infers a pattern fitting.
Yeah, that's one way to, yeah. It is. It is. It's mentioned that in a Klein bottle. Here's one way you can think if you didn't follow it. You start with this thing, this surface, and then I'm going to stretch the ends. And then, well, I can make the surface I just did, but I could just also glue these two things out. So gluing, it is a Klein bottle. Here are my mass interpretation. You can keep playing the game again and again. Well, I'm not sure you can see this one, and I couldn't bring it because it's too big. But you can have a Klein bottle and a Klein bottle inside the Klein bottle, like these dolls are one inside the other. And this is still a very, with more stuff. And what about this? So here I have a figure 8 across the interval. I twist it, and I glue it. Oh, this is a small one because here it is, the same thing. Pass it around, please. This is a Klein 2. And one way to see this is a Klein bottle is where you have a rectangle like this. I identify pairs of opposite edges. Now, we know that if we want to make a physical Klein bottle, it has to have intersect itself. And how come we're going to intersect itself? We choose. So what I'm going to do in this case is intersect along this line marked in pink here. So I'm going to fold it this way and fold it this way. So this forward and this back. I get this, then you twist. The arrows are going to coincide, and then you just glue it. So I'll say, explain a remark, this doesn't like, when you get your mind in particular thinking, which is not general enough, you make mistakes. So we have to keep in mind smart decisions. And then we have these shapes, and as John said, well, we can deform one into the other. One way to do it is, here is, I was to explain, here it's knotted. You can deform, if you allow the thing pass through itself through immersions, yes, you can deform this one into a standard Klein bottle. You can go between these two by an immersion. Yeah, that's one way. But what about this? Do you think we can deform it? Well, it turns out that you cannot. So the 4 classes of regular topic, these are the formation classes when you just, move through immersions. One is this figure 8 one, which is twisted in one direction. This one, hopefully you can see, is twisting in the other direction. This is the standard Klein bottle. And this one here, this is a Klein bottle, but here I have a dent twist, meaning that I just remove a cylinder, do a complete twist, and I put it back there. So these are different parametrizations. So I'm not forming the surface, but keep the parametrization, forming I've done more enough by parametrization. But with 4 classes, few don't care about parametrize because, after all, we care about the shapes. These 2 things, they are the same mode parametrization. So we have 3 classes. And now I'm going to talk about another wonderful Klein bottle. This is our colleague, Jenny Salmai, Glenn Lawson. And he was thinking the fourth sphere, I just found this representation of the fourth sphere. He gave formulae, three sphere in four space. Thank you. See, I marry well. So. So he started by, he constructed, he described minimal surface in the three sphere. And he has some pictures. These are the pictures because he just repeats this tetrahedron, copies them in certain ways. And then when they close, you get a minimal surface. But then, well, we can project it stereographically to R3. The surfaces. And that's a nice picture, by the way. When you project the surface, the one you get something that looks like this. It's really hard to see. I don't have a picture, and the things made are too big. One way to see it, something later. If you think of, I'll say with my waving hands, if you think of the figure 8 cross the interval is here, and then you make one end very big here, and the other end very big here. So small end big, and then you're going to twist and glue. You put it inside in some sense. I can later. Oh, by the way, this is an announcement. I'm going to show some of these things during lunch, around lunch, upstairs. And so you can see more, and I can explain better, hopefully. So here it's moving. Yeah, there's more pictures. And this is, again, a Klein bottle. And one way to see it is, what's that? This is the figure 8 cross the interval. So it's not the bottle like the other one, the one that is not bottle. There are two, well, depending on how you twist the Möbius band. There are two ways of twisting the Möbius band. So here I have two Möbius bands intersecting each other. And then if you glue this, I have an indication when you pass it around. If you glue this, when I hand this, you get the figure 8 that I showed you. If you glue it in another way, which is, just going from here, a little more complicated. Oh, here it is. So here you see you glue it, going there, then you will get done that is looks like the Lawson wine bottle. Catch. So here it is in 4 colors. And I was just playing with mathematics. When I discovered this formula, I just almost went blind with my computer. You can think of it this way. Remember, Klein bottle is a rectangle that you glue pairs of opposite edges in certain ways. And here what I'm going to do is glue, the colors indicate the gluing. And just to see things a little better, I have a paper that is colored here in blue and the other side in green. So this, when I flip it this way, I get that. So when you produce this gluing, here is the Klein bottle. I'll go over this. And then this stereographic projection. What you can do, well, is move the pole. And when you move the pole, you get different projections. And they all look so beautiful, I think, that I cannot not put it there. Here, there's a little bug in my program or Mathematica. But here is the pole moving. And when it goes, explodes, of course, it's like the pole isn't on the bottle. Here it is, just like two planes which are in the middle twisted in a way. All bottles. And, well, we could ask, we know some of these are regularly homotopic, but can I deform it, with an isotopy way? And in fact, this is, I was thinking of the evolution sphere for a long time. time, but it turns out that, I don't know if I can explain it really well. So here, maybe I need to. This is the Klein bottle kind of inside out. And here where I have my finger is a tube, and I'm going to stretch, imagine that I put more and more fingers here. I stretch it, and then I want to take this thing out, what looks like a bottle, and the tube that is inside would be the usual neck inside of the Klein bottle. So here I have like an intermediate step. I stretch it and I took the neck out, and maybe you should see the two things together. And when I keep pulling here, I get a standard Klein bottle. You're the catcher, 1 and 2. Sorry, I'm not a good thrower. So in fact, yeah, these two are isotopic. These are not even, there's no hope there. I suspect that, no, I want to say, so this is the long Klein bottle and this is like the figure 8. You can do a trick similar to a version of the sphere, but I suspect that you can deform it, and all these nights when I couldn't fall asleep, I thought I saw it and I was almost there, but I'm not sure, so I don't want to say things, but I'm almost sure that we can isotope one into the other. Now, so sorry, I need my water. So get my water. So now remember if you remember, or maybe I'm telling you for the first time, the Klein bottle is made, and there's a way that you might have seen, it was in one of the pictures. If you slice it in two by the symmetry, so here I have, see, 2 half bottles, glue them. This is a Möbius band. And this is a Möbius band here, which is crossed by, there would be, this is a Möbius band. And if I pull this out, which with self-intersection, but what I'm saying is these two make a Möbius band. There are more ways, Boson, Klein bottle, whatever. You translate, occasionally I say the wrong word. Now, here you see the two pieces. One is in dark color, and this is translucent. These are also two Möbius bands. Now, this was discovered in several ways, but this is a Möbius band whose boundary is on a plane. Silence. I have a few of them. So this, here is one. This is the projection of, half of these wine bottles. This one is a little delicate, it's sturdy. Oh, gee, wait, something happened. I got disconnected. This is in my thing. So there's a way to cut this, and then you cut them in two. There's a self-intersection. You pull them out, and you get these two Möbius bands with a boundary on a plane. Let's see. I know, I can't see, but let me see. So I made also, I'm back now. Oh. This is again a Möbius band, and you can, this here is a boundary in silver, and you can think of this going, forever. So this is a Möbius band with boundary on a plane. If you add a point and infinity, it's a Möbius band, right? Maybe, let me see if I do the zoom thing. Maybe I got out of the zoom. This should be an internet thing. I'll try. Oh, join a meeting. Join. Let's see. I'm trying to connect because I'm very picture dependent. This is me drawing. Okay, it's not connecting. And I have, I think, 6 minutes. 6 minutes? I know. Okay. So, well, have 6 minutes. Not. Oh, this looks. Okay, let me. I'm going to skip. I said I have a little. If I have a little time, I'll talk about the projective plane. Oh, I have one more Klein bottle that, for some reason, I skipped, and here it is. And since this conference, includes singularities, this has singularities. I didn't want to make everything we know singularities. So here, there's 2 points. The self-intersection is fine, but here there's, but you can think singularity is also self-intersection, but here are 2 singular points. And you can deform this into a standard Klein bottle too. Well, this fantastic surface I wanted to talk about, which is the Boy surface. Let me just as a top surface. We know that Steiner had a Steiner surface, and basically the way I think about it is, well, you know that the projective can be pairs of points in the boundary, but you can also do this with so, and if I manage to glue this hexagon in any way, so of course I will have self-intersection, but I can glue these things, what I get, if I do it in 3 space, I get a projective plane. Now, boy, I think to be connected. I don't know. Anyway, so Hilbert, the story, the legend, if you Google around, you will see Hilbert told his grad student boy, prove that you cannot immerse the projective plane with that is not possible. I tried to find some kind of, primary source that, really corroborates that, and I couldn't. And I asked experts, and so I don't know sure the story is true, but we do know that Boy found this incredible way to immerse no singular point. Again, if this idea, well, I have a small one again, limits of my carry-on. Here it is, and I can draw this is, I really need anyway. So it is, I can't draw this, I'm very slow drawing, but so you do this, you're going to do no, I can't do it. I'm not a drawing, I know I need computer and stuff, but the idea, he gave the sections of these curves, which are promised, they are only my slides, I can tell you more at lunch, and he made this surface. He made another one quite interesting too, which became famous. So painters and the surrealists like them, and it appears in books and collages, these other models. They are nice plaster models of these surfaces. And, let me see, I'm just thinking, what can I do without? Okay, what is Right, so this is not a Möbius band, it's a double twisted, and what I can show you just out of the top of my head, this is another not Möbius band. There's many ways to see, there's 2 boundaries, there's 2 sides, and this, we can arrange it to be the double cover of a Möbius band by, you have to put the sides together, which I Ta-da! So this is, and then here is the double cover. And you can also do something which is that I use to make this Möbius bands, which is that I'm gluing this shape that I have through one of the boundaries. Hopefully you can see. I'm almost done, so it's okay. Here I'm gluing it. And again, this is a Möbius band. So this is what I, when I said, you can ask myself, how can I make this Möbius band that claims surface? And I was a lot of which, in fact, type of thing, when you start with a zipper, my last thing, I promise. Here is a zipper, and I twist and I glue it with Velcro. And when I open this up, I get this, I have to glue one twist, very old Velcro. So when you open it up, you get something with 4 twists, 4 half twists, so 2 full twists here. Now, if I close the zipper, if I put the boundary of this thing, what was the boundary before in a plane, and if I close the zipper, I get a Möbius band. Well, I can't, but as a topologist, I can close the zipper by gluing a disk on the zipper. And this is how I made the Möbius bands. Oh. So you can see this around, my last thingy. Here I have a red boundary. There's a yellow band that goes twice around the yellow boundary, and then I just glue a disk on that boundary, and I get for, oops, thank you, this line. I'm done.
Well, here's one question.
During most of my life, I had this conjecture. Möbius did projective geometry when he was 18 years old or something like that.
1/8?
1/8.
Okay.
And then he invented the Möbius band when he was 8'1". Well, I'm not sure, but it's
68. 68.
Years old.
He was. He wrote. He presented a memoir for the French Academy for a prize studying polyhedra. He wanted to classify all polyhedra, but then he did only volume and he wrote a lot. The French complained, enough for French, but apparently it's a fantastic creative work, and there's a lot of ideas there. He also, I couldn't show it. Oh God, this is so cool. He said, well, for instance, let's make a Möbius band now. He did it by gluing triangles. So he had 5 triangles, like, oh, I have a blackboard. Something like this. And you glue it in the Möbius band way, and you get a Möbius band. And then you get a pentagon. You have 1, 2, 3, 4, 5 segments of band. You get a pentagon, you glue. And you say, oh, you get a surface there. It has Euler characteristic 1, so it's not one of the surfaces we know. And he left it there. But this is, projective plane hadn't appeared as a, sorry, I didn't answer your question. I started to blab.
Continue, finish.
No. It's just, it's amazing occurrence of the projective plane as a surface, but he didn't push it. He just stayed there. This is
Okay.
65, he presented his memoir, and then he published part of it.
Okay, so you already answered my question. What I always thought it was Möbius was working with the projective space. So when he was very young, when he was old, came the question of surfaces, non-orientable surfaces, and he said, of course. And he took the projective space. Boop.
The surfaces, they didn't appear as surfaces until later. Klein mentioned the Klein bubble. This is the first one that is really mentioned. Oh, this is a surface. Maybe you say, okay, this is nothing, drop it. Then Klein did it, and then He was a student of Klein, I think in 1888. First of all, the classification of surfaces, Möbius and Camille Jordan, they did works towards there, but not only orientable. And then later, Van Dyck, which is a Klein student, he did a classification of non-orientable surfaces.
Okay, so I was wrong. There's no connection between the young Möbius and the old Möbius.
But one thing is the projective space and the projective ideas, the other is the projective plane as a topological surface.
Okay, thank you.
Any other question?
What's that?
If you take an A, you take a cross curve with several loops,
Uh-huh.
an odd number of loops, and you do the same thing.
Yep.
You also create a Klein bottle, and they are isotopic. You can use quick-based theory to prove the regular homotopy of figures.
If you get an odd number of loops, you get a Klein bottle too, and then yeah. Yeah.
And then you
Mm-hmm.
suspend it like that, the orientation reverse, and then you have another Klein bottle,
Yeah.
and depending on the number of
Not all curves you can do it nicely, but anyway, it has to be a curve that has the symmetry.
if it's an odd number of
Well, you need to have the right symmetry, no?
exactly.
Yeah.
You see that, and then you have another Klein bottle, and
Yeah.
then you prove that they are regular homotopic by using quick-based theory on the plane. Quickly classify
Okay.
surfaces of the plane.
Right.
Maybe.
Nice.
And then one thing is that you can show that use the, I mean, it's well known, but it was so surprised to me that you use the void surface to invert the sphere.
Yeah, I know. Yeah, we have
That's a beautiful.
our colleague Anthony Phillips. Oh, Stony Brook, I can brag.
It's beautiful, no?
Yeah, it's amazing. Yeah.
You
Uh,
need to think that you
it's-
understand it. See?
It's in my to-do list of wire stuff. I have to understand it and make it.
What,
What's that? Can you come? Well, maybe one or two, but the more the boy get to choose, but you're not in 25, so.
any question? No. Any more questions? Well, let's thank the speaker again. Thank you. And we come back at noon.
Sí. Déjame sacar esto.
Patrick. Patrick. ¿Sí? Bernard. Tu m'écoutes? Non, 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 reste là, reste là. Je voulais voir si tu m'écoutes. Hein? On t'entend? Oh. Bueno, bueno. ¿Qué buscas?
Henri Poincaré, 1854.
Ah, no, no me puedo,
Henri Poincaré.
no me puedo ir tan lejos. ¿Sí pongo? Nació, fue cuando nació.
Fue cuando nació, nacimiento 29 de abril.
Ah,
Deja mis prints.
¿no tienes nada de 1974? No. Bueno.
¿Listo?
No, bueno, sí, pero si los celebramos hoy, en su año.
94, Cyber Witten.
¿Mm?
Cyber Witten in 90. Cyber Witten, 94, 2004, Perlman.
Perelman, what?
Perlman, Poincaré projection. Proof.
Oh, but I had nothing to do with that.
Okay.
But Pepe said Poincaré.
Okay. Our next speaker is Santiago López de Medrano, and he is going to talk about the intersection of ellipsoids and singularities 1.
Thank you. So it's great pleasure and honor to be in Pepe's Fest. We're celebrating where is it? I got it wrong again. You were born in this year? Yeah, okay. We're celebrating Pepe's birthday. And there are many things that I want to celebrate, that I'm celebrating this year. Many have to do with Pepe, but not all of them. 1964, I went to Princeton, and there I met many nice people, especially Bill Browder and Dennis. Is that all right? Yeah. And many more very nice people. We had a lot of good friends. Many of those good friends are now no. No. Some have died, but some are still great mathematicians. I could fill up the blackboard with that. And turns out that in 1934, Browder was born. So he is 90 years old now and still working. I see him almost every week through the Princeton topology seminars, and he's always there. He's one of the organizers, and he always has something to say, and so on. I recommend that seminar. Sorry? No. Oh, he's 90. He's still alive. Just to mention that. And then Dennis and I, we went to Browder's course. We worked with him. He was our advisor, our common thesis advisor. I did a not bad thesis. I solved a problem posed by Browder, and it became a book that 50 years later is still giving me citations, and it's remembered. Last citation is in a book about the Abel Prize winners. I appear there. So I did all right. But then Dennis also wrote a thesis with Browder, and with that thesis he revolutionized surgery theory. Both our theses had to do with surgery theory as a branch of differential topology. And Dennis revolutionized surgery theory. Then he revolutionized algebraic algebraic topology, and then he revolutionized dynamical systems, etc., etc. And I lost track of what other things he has done. So we've been friends since then, and that's and we don't see each other very frequently, but we're still friends, I think. Okay, Then I came back from Princeton. I still did some surgery and differential topology for a while, but then I wasn't happy with what I was doing. Surgery theory itself became very algebraic. Question of computing wall groups and new wall groups and quasi-wall groups, and which I didn't like too much. This is what it was about involutions of spheres, and then there were papers by Hirzebruch about involutions of spheres, and papers by Atiyah on involutions of spheres, and I thought I had to do something different. So also coming back to Mexico and having students make this to do surgery theory and do something new on surgery theory looked like a very difficult thing. So I stopped doing surgery and differential topology, and I tried some singularity theory, some mathematical biology, dynamical systems, different things. Also, I was very busy with teaching and the trying to change the educational systems in preparatoria, and I was doing many things, and I had almost forgotten differential topology. Then something happened. In 1984, there was a in our institute in Mexico, there was a seminar organized by Alberto, Pepe, and Javier. Seminar on dynamical systems. And there I started going to that seminar, trying to learn something about dynamical systems. And then one day, early in 1984, January, I think, Alberto gave a talk about complex dynamical systems, the work of Camacho. It was about something very simple, system of complex equations. Very simple system. You can write the solutions immediately, but there's a lot of geometry and topology hidden in that simplicity. I will talk about this. Well, just to finish this, in 2014, there were No, I'll speak later. Okay, so Alberto said, mentioned, explained the theory of these systems, and asked the question. I can only draw the real version. The solutions of that system, the corresponding real system were of this type. Well, there were those that where all the solutions went to zero, but there were those where there were different types of solutions, like this. One solution is zero, the other one is the half-axis were other solutions, and then there were these solutions that never got near the origin, and they were called Singularities. And if you take the space of leaves, identified each leaf to a point, then you have a problem because you obtained a non-Hausdorff space. You take this point, any neighborhood of this point intersects infinitely many of the other leaves. A neighborhood of this guy touches an infinitely number of these leaves, etc. If you have a nice space, then you restrict to the single leaves. And how is the space of the single leaves? Well, they have a property that each single leaf has one point that's closest to the origin. So the space of single leaves is like looks like the union of these two lines in this case, without the origin. So it's a nice Hausdorff space. It's conic. So it's a good idea to intersect it with a sphere, and you get a manifold. In the general case, you get a manifold, and the manifold in this case, if you do it in the manifold is spheres. In this case, it's S0 cross S0, 4 points, and this is the manifold. So in this case, you know everything easily. The complex case is more complicated because has the same problems as before, but it happens that when these single leaves tend to the axis, they don't go straight, but they go around, turn around the nut. And the way they turn it around has to do with these coefficients and can be very different. So there are many. In the real case, this is a finite number of points.
Why is it S0 cross S0?
space of Siegel leaves is this cone, and its intersection is S0. You just have to write the equations.
You have to assume that the values are in the Siegel domain.
Yeah. We're in the case that not all the solutions converge to 0, and then you write the equations. You find the equation for these points, and you write it, and you get the equation of a no projectivizing. I write the equations. And I compute what I can write the solutions, and I can put which points in each of these solutions goes to 0, and then I obtain something like this. A cone like this. Okay, and intersect with the unit sphere. And you can see dependently how many of these are positive, how many are negative, you get a product of spheres. Well, and in the complex case, it's more complicated. And that was the main part of the work of Camacho Coit-Purpalis. Oh, I'm almost finished. And so they have a topological classification of all cases, and that has to do with the way that Siegel leaves turned around in the limit around the lines. Okay? So here, this equation, you can assume these are +1 or -1 without changing the picture, so you get the two equations of spheres, and you get a product. Okay, and the question was to determine the topology. The question by them was to determine in this case. And that was not as simple. They couldn't do it. They left it as a problem. And in that seminar, Alberto said, here's the problem for you. You are going to solve this problem. Many years later, he confessed that he was hoping that in the next seminar, 1 week later, I would be there with a solution. Well, it took me practically the whole year to obtain the result, and some more time to check all the details. But I proved that I obtained that. Let me tell you about it. Okay. So what I did was, first, so we have that. It's given by, we have the coefficients, we looked in C, and there were some various steps. First, determine the smooth. When it's smooth, and it turns out you have to avoid this situation that two of these coefficients have the origin as a convex combination, smooth. Then once it's smooth, well, you know, you can move the points around as long as you don't this. Skip the, never go through a point like this. And the second part was to obtain a normal form. One can put together these coefficients. If you don't break this line, you can actually put them in the circle, and you can put them as the vertices of an odd polygon, a regular odd polygon with multiplicities. And then the next step was, well, given the normal form, try to find the topology. So in this case, the topology of the manifold is given by sigma lambda I ci square equals 0, and then one intersects with this equation, with the sphere, and so you had M, a polygon with M points and multiplicities. When M is 3, it's easy to solve. You have like 3 equations of that type, and for M equals 3, you get a product of 3 spheres. It's just a question of adding and subtracting equations, like in high school. But the other one looked a bit difficult. It took me some time. By the end of the year, I went to IAHES, invited Venice, and there I had time to work on it, and I had time to look at the bibliography, and this is actually three real equations. When you take the real part and the imaginary part, so you get the 3 equations, and there was a question of so simple equation. I thought it would there's something that should have been solved in the early years of the 20th century. So I was looking in the bibliography. At that time, it meant pulling down a math reviews book year and follow the search, and I finally found a work by McGavran. Dennis McGavran, who studied actions. This manifold has an action of the torus, Tn. And this guy has studied actions of tori on surface, on manifolds, and he had discovered that there were some that were connected sums of this type, connected sums of products of spheres. Yeah, the whole family. Only one of his cases was one of my cases there. They were, for the rest, they were different. But then I had the idea that this would be a connected sum of spheres, of products of spheres, and I finally proved it. The proof, how much time I have? 2 minutes. Okay, anyway, the proof meant the way to, as Milnor told us, to understand a manifold, it's very good to find a manifold it bounds. That's how one studies spheres. And so I looked for a manifold whose boundary was this. And it was very easy. You take a new variable, real variable, and write this, and then this gives you another intersection of these ellipsoids, and and then you take just the half of it, and that gives you a manifold whose boundary is the one we have here. So I could do this, but this took me out of what I had studied, because here I had complex equations, even if they have squares, and this was a real part. So I had to go back and do all the work again for equations of this type. To repeat all those steps to understand the real case, and then to understand the half of a real case. And I finally found a nice cobordism, could show using the H cobordism that one obtained precisely connected sums of products of spheres. Okay. So I solved, by the end of the year, I solved Camacho-Kuiper function question. But then, why not study the real case? And it turns that in the real case, you could do the same, but you could not apply the H-cobordism theorem, because there were cases where it was not simply connected with a small, they had a low dimension. So I had solved this general case, but with some exceptions. So may I have 2 minutes to finish this? So many other things happened. So I solved that up to some cases. It took me many years to do special proofs for the remaining cases. Then there was another very important thing that Alberto observed, that if we take this manifold, this is, okay, no, I've skipped many things. I'm sorry. There's an action of the torus on this. The action of the torus of this, the quotient is a polytope of the same dimension, which is in this case n minus 3. So this you construct you obtain the polytope, and from the polytope you can get the manifold. So there was a polytope there that was very important. And Alberto observed that if you take the quotient, this is in Cn, actually in the sphere, and if you go to Cpn minus 1, you obtain a complex manifold that it's that has it's a complex manifold, but is not a holomorphic or algebraic or anything submanifold of this. And this gave from this we constructed an infinite amount of complex manifolds that are not algebraic, are not Kähler, anything. So we obtained this, and for a time that was the people in dynamical systems said, okay, the problem is solved, but nothing happened. That much happened, and this was very people in complex geometry interested because there was an infinite family of complex manifolds that are not Kähler. The first one is the Hopf manifold, which is S1 cross a sphere. But it was an enormous generalization. So there was much work about that. They are called now LVN manifolds. This is me, this is Alberto, and this is Laurent, who is here. It had many consequences. Well, I have no time. I want to say for a long time, algebraic topologists didn't look at these guys until there was discovered a theory called of polyhedral products, studied by Sam Gidler and others, and it turned out that these objects were special cases. With Chaperon, I did some dynamical systems. I studied some dynamical systems associated to this. Sort of Hopf bifurcations of higher dimension, and so I did some dynamical systems using this theory, and after it was discovered that this was connected with this theory of polyhedral products, then it became, all this work became very, very, very appreciated by algebraic topologists, and so starting by Sam, and since then there has been a lot of work about them. LVM manifolds are well known by topologists. I have I have been at a conference where the speaker writes LVM manifolds. And at the end, I said, I'm L. Introduce myself, I'm L. And I think that they have become kind of a normal thing. And so people speak of LVM manifolds without quoting our work. And well, here I just want to write. I'm over time. This is Zaragoza. When I gave a talk about all this in Zaragoza, they asked me, Enrique, who's here, asked me, no, you have to give us a whole course. I gave a whole course, and since then we've been working together. Something else happened with Pepe became director of our institute, and when he started, I told him, I have a very short list of good directors of the institutes. I'm sure you're going to be one of them. And I was right. So my list of good directors of the institute was increased. Pepe is here also because we have his party in Mérida. And here we have Pepe 60, and I have Pepe 70. Okay, so there's a lot of things I left out, but in all this part, Pepe has had an important role, and I thank him again.
Well, we don't have time for more questions, but since the next talk is the second part, maybe at the end we can ask more. So in 5 minutes, we come back.
Sí. ¿Me se oye? ¿Me se oye?
Well, our next
Yes.
talk is by Enrique Bartolo, and he's going to talk about intersections of ellipsoids and singularities too.
Okay, so thank you very much for letting me speak here. So I'm going to give the second part of, so this is a joint talk with Santiago. And okay, I took this t-shirt because this is to show a background about the time where I met Pepe. So just 10 years ago. No, this is a very bad background because I think we met. Our hair were much different in both cases. So I think I already told this about in Pepe Fest in Mérida. I remember a very nice talk, and I don't remember if it was you or Alberto or Le, because it was about a work about conics, basically, quadrics, but conics in P2. So with this in principle, what do you say something new about this? And they said not only something new, but something very interesting. Of course, putting together Le, Pepe, and Alberto, it must be something very nice. And okay, this idea of this simplicity is what I took very nice from these problems of intersections of quadrics or ellipsoids of coaxial, because in principle, so this problem that came from dynamical systems, it can be written in a very simple way. So we want to understand intersections of these ellipsoids in Rn. Okay, we can make some simplifications because just making.
This comes from actions of higher dimensional linear groups on CN.
Okay, so here we can just do the first ellipsoid. We make homothesis in each variable to make this sphere, and then we can do this, homogeneous. And in the part that Santiago didn't talk, not yet. Okay, this is a very nice thing that finally everything will be interpreted in this tuple of points in Rm. This is the way we are going to parameterize intersections and understand things about this. They are not, there were ellipsoids, but okay, we can just subtract the equations and then we get zeros. So the system of equations is the same, but the solutions are the same, okay? And you see everywhere there are squares, and these are the polytopes that Santiago talked about. Just forget squares, because here we have some linear things. And basically, okay, this is like taking squares, and then you can put signs everywhere. So this is like study topologically the first orthant of these equations, and the first orthant here is the same thing. So topologically you obtain this Z by making reflections along any coordinate hyperplane. Okay, so we have these intersections, which may be very complicated, as Santiago said. We are going to parameterize either by these guys or by these polytopes. So these polytopes make a translation of the problem, so we will take some combinatorial properties. Huh?
The way you're writing is a torus and using a
It's, a torus, it depends.
at a point, I pick one of these.
Yeah, this is not, we take only the positive part, it's not.
Oh, it's only real.
It's only real, okay, and then the other guys, okay, sorry. So actually, and so there was this picture here. So from this point of view, this AI, so these solutions one can interpret, okay, so we take all the possible convex linear combinations of the zero. This is what defines the polytope, and it will be useful there. And this polytope, exactly the intersections, the faces are in the coordinate hyperplanes, and this will be served to doing the reflections, okay? And this is, so finally, topologically, this polyhedra, this polyhedron contains all the topological information of the guy. Okay, after, so one of the things that Santiago didn't talk, that I think in Merida or around Merida, so he asked, okay, it will be, so, okay, maybe I can, okay. There is this condition that is called weak hyperbolicity, which in terms of this A says, okay, of course, 0 will be a convex linear combination of some points. As he said here, it's very bad, it is just very few points. Of course, here for 3 points, in general it will be the case, but 2 is very bad. So he said, okay, as far as they are not as the same equation of the number of equations, then this is it will be the condition to be the intersection smooth because of transversality. And then Pepe asked a question, okay, this is an if and only if or not. So the answer, so there is no Galician people here, is yes and no. So it's, and because the answer is basically yes, once you assume that there are, for example, non-degenerate conditions. So because of course one can repeat one equation a lot of times because you have plenty of equations, but actually you can take a minimal, okay? So this is, so this can be expressed in terms that, okay, so you may have this generator system, and then there is a lot of convex geometry for this AI, so you can, as Santiago says, to put in here, but okay, you cannot move in order to make that these linear combinations of the origin changes. So it's, okay. And all these kind of things from the point of view of the polytope, so what does it mean? Okay, it means basically 2 things. So one, if our polytope must be simple, okay? Of the vertices, the link is a simplex. And not only that, but they have to be exactly, they have to touch exactly the dimension of a hyperplane coordinates. We'll see later. Okay, so this is the case of the smoothness. And so after Pepe's question, Santiago wanted to study also the singular case. And since he came to Zaragoza, and I'm very fond of singular cases, so we started to work together. In the first slide, there was the third collaborator, which is Maite Lozano. So it means that I'm the youngest of the 3 authors, which is just now the only possibility for me now. And so when he talked, so some of the fact that everything we had this connected sum of product of shears came from H-cobordism. So Santiago is claustrophobic for small dimensions. But then with Maite Lozano, who is an expert in geometric topology in low dimensions, then we try to study also small dimensions, okay? And, okay, so you wanted to understand singularities. When asking complex geometry, the first thing to study, with, for example, with Picard-Lefschetz is the non-degenerate singularities. So we wanted to look for the mildest singularities, okay? So I saw this WH condition. It was that the origin was not a convex linear combination of m points. So here it means that, okay, we are going to allow something, but not so much, so just one less. Or from the point of view of the polytope, okay, maybe it's not simple, but at most, so for example, in 3-dimensional cases, you may have, for example, the simplest can be, the link can be a polygon of a square, a quadrangle, not much. No? So this is, okay, and then we want to study this. So the project is to understand all the singularities, but probably the generic ones are the first ones to be studied. And some of they already, so I start with, and easy example in this case. It's stupid. So we have two equations. So the sphere, the circle, and this equation. Okay. Here the solution is S0 is 0, and the only positive solution is this one, which in that case is the polytope, and then doing all the 4 reflections, and we have the 4 points, and of course S0 times S0 is smooth. Okay. Okay. In order to do some other examples, there is something very nice that was done by. So if we add zeros, so one of the points is the 0. So basically, there is a variable that will appear only for the sphere. Okay, so what we get is a suspension. This is an easy exercise, but this will be useful to, for example, in that case, another example could be done even in one dimension. So we have S0, and if we take 2, we have S1, etc. So this is and for example, in the other case, we have S0. If I add S0, then I have the suspension. So this is, we can see also as the bipartite complete graph between 2 and 4. And in that case, this is the polytope is simple. I mean, one polytope must be simple, but you see the faces are in hyperplane coordinates. This is good. This is only in one hyperplane coordinate, but this is not well put in some sense. And this is what is given these singular points. Of course, here we have smoothness, but here it's not the case. Okay. So this is more or less the same case if I want to do two generic singularities. So basically the point, as you take 4 points, and here I see that there are 2 points where the convex linear combinations are less generic than expected. So this is a drawing in dimension 4. And here the 2 vertices are bad placed with respect to the hyperplane. And here we have, this is the, topologically, this is the intersection. Okay? Okay, this is more things that we can get. For example, in that case, like this double torus. So because of the reflection, the singular points may come in tuples or 4-fold or 8-fold. In general, it depends on, okay. And we have more examples. So this is something, okay, these are abstract drawings. Okay? By some reason, I'm not able to draw in dimension 5. So okay. Okay, so for example, one of the points that interested Santiago is what happens if we deform the points. Okay? So in the smooth case, if we deform a little bit the points such that the origin does not cross through the new points, okay, using Ehresmann's arguments, we have that the intersections are diffeomorphic. Okay? What happened in the singular case? So in the singular case, okay, if we make equisingular deformations, what does it mean in that case, equisingular? Basically, it means that all the combinatorics of the complex linear combinations or the combinatorics of the polytope, not the polytope by itself, but the polytope with the intersection with the hyperplane coordinates is the same. Okay, in that case, still, so we have homeomorphism. Not clear, I think even not clear. In general, we won't have a global diffeomorphism sending one to the other. So for example, I think the other examples we may have some cross ratio in the singular points that avoid diffeomorphism, but we have homeomorphism. Okay, so we have singularities. We would like to do resolutions, but it's not the good language, because a resolution is usually, is a proper map which changes only in the singular points. So in this theory, what is best done is smoothings. So yes, look for smooth guys that are close to our guys, and then Of course, we are in the real case, so one of the questions is maybe we have topologically different smoothings that we don't have in the complex case.
Do you have always smoothings?
In that case, yes, because basically there is, yeah. So for example, think about you have endpoints. So maybe there are bad convex linear combinations of the origin. As far as you move a little bit, then the linear combinations will be standard. Okay, but it will depend how you move. You may have different topologies. Okay. Actually, so there is a point that Santiago didn't talk. Let's say, so in that case, when I am in Rm, if I have a singular point, then this means that I have an affine subspace of is affine but contains the origin, so it's a linear hyperplane where I have these linear combinations. Okay, but I have more points, and then this goes to the positivity and negativity. There are some points that will be some pi points that will be positive, some qi points that will be negative. And, okay, this will be that the singularities that we are obtaining, they are, take the spheres, these spheres, take the product, and all the singularities will be cones over these guys. So, of course, there will be singularities, because they are not cone over a sphere, but over a product of spheres. And looking in this way, okay, there will be 2 to the power m because of the reflections. There are plenty of them. And looking at this case, we can understand topologically which will be the smoothings. And the smoothings, okay, so will be instead con of the product is con of one factor times the other one. And then we have 2 choices. And basically, this is what we are going to do the other way from the polytope. So, at the polytope, we are going to move in one direction on the other direction, and this will be these two possibilities. Okay, and it means that in that case, okay, we have 2 to the power r options because we have 2 choices in each case. Okay. Okay, so for example, in that case, I had this singularity. Okay, here either I connect with a tube or I close with disks. Okay, and what I do in this singularity, I must do here. So here, of course, we have this is one smoothing, and this is the torus. This is the another smoothing. Okay, and in the, for example, if we have 2 generic singularities. Okay, here we have I can do just like this case everywhere, so I have this one of the smoothings, or I can combine the 2 possible smoothings, or these are, okay, we have probably more, but they can be repeated, okay? I have another one where it can be exchanged. Okay? And now this is in our work with Maite and Santiago, okay, so we want to understand what happens in dimension 3. And in dimension 3, we have 2 types of singularities, S0 times S2 or S1 times S1. Okay, so the cones is, again, is either to fill balls or to, so for the singularities, to fill balls or to make a tube. And for dimension, for the case where it is the cone over a torus, basically, okay, we have 2 possibilities, but here I don't really have a torus. I have a product of 2 S1s, so it's either a closed one, so put in a torus such that one of the fibers of the factors is the meridian or the other one. Okay, so these are the 2 possibilities. Okay, we are mostly interested in the 1-1 because the other singularities are much it's easier to how okay. So in that case, what we are going to do is, okay, instead of starting from these equations, let's start from the polytope. And consider a polytope, even put your polytope in any dimension, but then now put your polytope in Rn, where n is the number of faces, such that each face is the intersection with one hyperplane coordinate. This can be done easily with equation. And this is what we are going to study, because this will give some of these intersections. Okay, this is what I thought. And okay, there are two possibilities. Either we have this link. Okay, when we have the reflections, the reflection of this triangle is a sphere, so we have the smooth case. Or what I will call vertices is where you have, this is the link, and when we do all the projections, so if we do all the projections, we'll have 16 squares, and with the glowings we have a torus. And this is the torus, and we have the directions that gives us these things. And, okay, what I was saying is that in order to obtain the variety, what we do is reflection. I'm going to consider the polytope not just as a polytope, but an orbifold. Okay? So the faces will be mirror of the, because I will consider not, I have a chart like this, but like I have the reflection. So we have an orbifold theory, and we can do, okay, for the fourth triangles is a little bit, we have to admit orbifolds whose spaces may be singular, but, and I mean, one of the advantages of this language of orbifolds is, I mean, I like very much when I was a student all the theory of covariance, because all the relationship with groups or everything like that. And of course, but when if we want to do something interesting, we have to consider ramified covers. And okay, then the relationship with groups is less clear because we have to take out. But if we consider, when we do these ramified covers, we consider it with orbifold language, then the orbifold covers have exactly the same theory that the other theory. So we have, for example, that when we have an orbifold cover, the orbifold subgroup is the orbifold fundamental group of the cover is exactly a subgroup of the other one, and if it is regular, it's a normal subgroup, and there are actions, which ways where it appears. Okay? So we can consider that this map, this reflection, is an orbifold. And basically, this map, this is a manifold, and we are forgetting the singularities in the best case, or putting just the singularities in very few, in very big codimension. If we want to forget the vertices, okay, I take my polytope, so I now will think this polytope is something that the vertices are at infinity. Then once I took out the singularities, then it becomes smooth. And it becomes smooth, but this is a smooth manifold, which is non-compact, and we can count the ends, and the ends are torus. So if we complete taking the cone over a torus. We'll come later with this. Okay, so let's consider the simplest example, having a 4 vertex, which is a 4 pyramid. So what are we going to do for the smoothing? Okay, what we want to do here is, okay, just either adding here an edge which connect these guys, or the other case. So here what we have now is a triangular prism in that case. And okay, so if we look at the varieties here is suspension of the torus, so we'll have 2 singular points. And if we take out the singularities of the vertices of the suspension, then we have this product. I prefer to put like this, because in that case, I mean, this is stupid, but this is a complete geometric manifold of flat manifold in that case. And the two smoothings corresponds to here, so the variety, this product structure is S2 cross S1. So we are, in that case, in both cases we have the same thing, but there is a zero surgery that connects both of them. So we can pass, we pass from one to the other. Okay, so this is a nice example. So we consider a triangular bipyramid. So these are the points, and here the three vertices, the three bad vertices. So I consider the three bad vertices corresponds to the fact that here this is a regular hexagon. The origin is in the convex linear combinations of couple of tuples of this. And if we move a little bit the coefficients, of course we have plenty of smoothings, but actually all smoothings corresponds to this case. So in that case, the origin is at most the linear combination of convex linear combination of 3. Okay? Actually, what we can do is move. So move two possibilities to move the 4 vertices. So we have then vertices, so we have 8 smoothings, but there are a lot of symmetries here, so this group acts, and actually we have only 2. So the first one, so this is the regular the bipyramid, but with the stereographic projection. Okay, the infinity is smooth point of the middle triangle. So here we have the 2 triple points, and what we do here is to eliminate, to make that this polytope is simple. Okay, this is the case. In that case, we obtain a cube, and this red corresponds to the new edges we have added. Okay, the cube, the top, the manifold is the cube, is the torus, and we have basically another possibility. So here I change the thing that we connect. And I do not know the official name of the result, but this is we could a pentagonal book. This is the edge of the book, and okay, this is the other result. And okay, you can trust me. What we obtain here, I mean, this is because one of the options also is to see this space of a tetrahedron where we truncated two vertices. And the result here is, again, as in the examples of Santiago, we have connected sum of product of spheres. And, okay, if you don't trust me, you are right to do that. And you can trust Santiago and Bossio and Messerman. And there is a way, okay, whenever you have this a polytope, you truncate. So which will be this manifold obtained from the new polytope. So it is not complicated. It will be the connected sum of 2 copies of the former polytope, connected sum with a lot of S2 cross S1. Okay, I'm going to skip the proof, but the idea is the fact that when you do connected sums inside the connected surface is like making connected sum with S2 cross S1, and this is the reason. And this was, okay, there is also another way. So I was talking about these orbifold covers. So when you take a polytope with, say, n faces, what will be the fundamental group? The fundamental group is generated by one guy for each face. These guys are reflections of order 2, and if the 2 faces are not disjoint, then these 2 guys commute. This is basically what happens. So here, all the faces are pairwise not intersecting. So this means that this group is abelian, but I'm doing a covering of this guy, so the intersection is simply connected. Okay? This is the intersection, so if erase these points, then this face does not intersect these other guys, so we have only the intersection between upper and down. Okay, I'm going to skip this, but there is a way to obtain this space, and this is, so this cube is the, think about the three torus as the identifications. So pick up one fiber in each direction, and so we are going to take the cover, this cover ramified along this guy, and then this is how we obtain this space. So this will be a manifold with torus ends because it's the complement of a link actually in a torus. This money, I think, yeah. This is related to the, because there is an orbifold structure that even in a metric way, and that's one of the points that actually this guy has a complete orbifold structure. Because there are, I don't remember the name, there are some Russians that did it, that you can embed this polytope in the projective space such that the four vertices are at infinity, they are virtual vertices, and this gives you a complete orbifold structure. And when you do the reflections in order to avoid the singularities, then you get a manifold, and this is the case. So our manifold has a complete orbifold structure that makes the connections between apparently two different ways. Okay. So I wanted just to end, there are more cases, but to end with the octahedron. So in the octahedron, I'm going to do the same kind of thing. So for example, this is apparently the Borromean ring, but it's not. This is if you do the stereographic projection of the octahedron from the center of a face. This is combinatorially. This is what you get for the face, for the edges and vertices of the octahedron. And so the idea here is, okay, at each point I want to connect. I want to make simple. For example, I can do like this, or there are plenty of conditions. Okay, so in that case, because for each one of the 6 vertices we have 2 options, so we have plenty of smoothings. But again, the octahedron group is acting, so actually we have only 7 possible smoothings. So in particular, we wanted to check, okay, what happens with the topology of these smoothings? Actually, we wanted even what happens with the topology of the smoothings with the link of the, but this is already too complicated. So for example, this is one case. So take a cube, one of the options, you take a cube and you truncate two vertices. And from the result I get there, so this is again connected sum of product of spheres. So S1 is 1 is 1 or S2 is 1. Okay. Here the truncation is in one of the bases. This is another possible guy, which is scutoid. This is what happens. It is in the cells of some flies, fruit flies. So this is actually something that appears in nature in this scutoid. It was discovered by some people from Sevilla. And in that case, so okay, this is basically again we have truncated something, and this is what we get. So this is S5 is the surface of genus 5. Okay, we have also this truncated tetrahedron. We have also this huge number of connected sums. The solid Durers also appear in that case, and the solid Durers is also a bitruncation of the cube. So the combinatorics of these two polytopes is completely different, but the topology is the same because truncating we had Okay, this is easy hexagonal proof. So this is for an hexagon, the intersection is the closed surfaces of genus 17 times S1. And okay, this is just the last case, and this is okay. The name, I will explain the name later, but I have no time to say the name. So as you see, one can see this, take this pentaprism, and this is, so in our paper, you say that we biselamos this face, and this is what appears. But it appears, I said 7 smoothings, it appears in 2 different, so the polytope is the same, but the new faces are different. Actually, we have a huge discussions because Maite said we have 6 smoothings, I said we have 7, and we were both right because it's okay. Why I call this 0? Well, that because I can cut this from this side, and here I have a pentaprism, which the bases are here, and I have another pentaprism, the face here, and I am gluing through a face, but to it. And the interesting point for me is that this manifold is completely different from the other guys. This manifold is a graph manifold, and actually, probably I'm not to define a graph manifold, but I can say you what it is. So consider 2 or 1. I mean, it does not depend. It does not have algebraic structure. Consider elliptic curves. I mean, so torus. Consider the product, and in the torus, take 4 sections and 4 fibers. So this is a curve in a surface. And now consider a regular neighborhood of this curve. And take the boundary, which is a 3 manifold. Okay, this is this 3 manifold. So this is, of course, how do you construct a regular neighborhood? You take a regular neighborhood of each curve, which is a S1 fiber bundle. In that case, it's even a product because the Euler number is 0. And okay, when you consider this here, this in the boundary, so you are plumbing, okay, and this is the idea. Yeah. Yeah, that's exactly that. And this 3 manifold, it appears to be this one. So it takes a while to see this, and this is the graph. So this is a way of, this is the reason of the, so each vertex is an S1 bundle, and each edge is a plumbing, okay? And this is the way, and this is very far from the connected sums of product of spheres. So it means, of course, because H coordination is no more true here, that we can have other things. So this is, and okay, in that case we can compute. So the fundamental group of this guy is a billion. And again, we have a complete structure, because we can put this octahedron in the hyperbolic space. And actually, there is a relationship between, for example, we can that way this complete, so it has a finite volume, and there are relationships of the volumes of all these guys. And felicidades, Pepe.
Well, since we are running late, we make questions privately.
The icosahedron is smooth, like because the vertices are. No. Excuse me. No. This is okay. This is the dodecahedra is smooth, and then we studied already, and again, this is in that case it has also a hyperbolic structure. And okay, we can, we can understand its geometry, but especially looking at the dodecahedron as an orbifold. This is what allows to understand it. Okay, and for the icosahedron, okay, we have in that case the singularities are isolated, but they are no more generic. In that case, the cone is so the singular points are cone over surfaces of genus 5. And then the combinatorics of the smooth things are much more involved.
Well, let's thank the speaker again. And we continue straight away with the next talk. We will be online. Hola Javier, ¿me escuchas? Hola Javier, ¿nos escuchas? No, nosotros no te escuchamos. A ver, ¿tú sí nos escuchas, Javier? Digo, nosotros creo que no te...
Yo os escucho.
Que ya, perfecto, muy bien. Muy bien.
Ahora sí.
Entonces, si quieres compartir tu pantalla para poder...
Ajá. Lo que no oigo a la audiencia. Si hay una pregunta, no la oiré. Me tendréis que pasar el micrófono.
No, tengo aquí el micrófono y se los paso para hacerte preguntas.
Entonces, ¿empiezo la plática?
Sí. ¿Le puedes subir el volumen?
Ajá.
Sí, pues comparte tu pantalla. No, te presento para que comiences.
Preséntame y luego comparto la
Perfecto.
pantalla.
Entonces, our next talk is by Javier Fernández de Bobadilla, and he will talk about symplectic geometry of the degenerations at radius 0.
Well, thank you very much. It is a pleasure to give a lecture here. I am going to try to share the screen or to share, in fact, not the screen. What I want to share is a window. I am trying to find the way. So I'll share the screen because I don't see the way of. I see. So let me start. So let me start by the important part of the presentation. So first of all, I would like to congratulate Pepe for his birthday. He visited me in Bilbao for 6 months, and it was a really nice period. And as you can see in the picture, he became a real Basque. So now I'll start with the serious part of the talk. It's a pity because I cannot hear you. So let's see. Now I will share a screen again. So there is something that is not. Yeah. So can you confirm that you see the blackboard?
Yes.
Okay, so let me start right away. So I know that there is a delay in the conference and you are tired, so I'll try to be as brief as possible. So I promised a general description of symplectic Ocampo space and applications. Okay, and this is a joint work with Thomas Pelka. Okay, so the the idea of a Campo space is classical, and it is described in a Campo paper. Where he computes the zeta function of monodromy. And it consists in creating a monodromy at radius 0 whose topological dynamics is very, very special, and this allows to compute the zeta function. So what we have done is to enhance a Campo space with a C infinity and a symplectic structure, and to derive consequences for this. And the two main consequences are a proof that a mu constant deformation is equimultiple, and a construction of Lagrangian torus vibrations over a codimension 2 over the essential skeleton of a maximal Calabi-Yau degeneration, except in codimension 2. Okay, so the first problem is better known to the singularities community, so I will center myself in this problem, but I would like to mention that this problem is motivated by the Strominger-Yau-Zaslow interpretation of mirror symmetry. Okay, but since I don't have so much time, I will focus. I'll try to focus precisely in the mu constant deformation problem. So I was planning to describe first the Campo space construction, and after trying to derive for it the proof of mu constant problem. But what I am trying to do is to be as brief as possible, and to describe the route to the proof of equimultiplicity of mu constant families in the fastest possible way. So let f from Cn times C to C times C, so we send holomorphic, and let me define f t of x as so let me write x t going to f t of x comma t, and let me assume that the Miller number of ft is constant. So it does not depend on t. So I will recall classical result of Le-Ramanujan. Actually, probably the easy part of it. So I don't need the part that uses the H-covariance theorem. Okay, so let me picture the space of parameters. Let me take a Milnor ball for the function f0. So this is f0 minus 1 of 0, and let me take a Milnor radius of some radius delta. And now I keep exactly the same radius, epsilon 0, and I'll take ft minus 1 of 0. Yeah, and everyone knows that it is not known that the Milnor radius is stable in a mu constant deformation, so perhaps the Milnor radius for the function ft should be smaller, ft. And now you can consider ft minus 1 of 0. You can intersect with b epsilon 0, and you can subtract b epsilon t. And this defines covariance. This is a homologically trivial covariance. So this is the first result in proving that a mu constant family is topologically trivial, except in the surface case. The surface case is not known because of the lack of H-covariance theorem, but we will not need it. And what means homologically trivial covariance? It means that if you compute the homology of ft minus 1 of 0, and now you subtract the origin, and you do it relative to ft minus 1 of 0 intersection the radius, the outer ball, this is 0. And this formula will be very important for us. Okay, so this is the ingredient from classical singularity theory that we need and that we will need. Okay, so let me mark this as Formula 1 and proceed. Okay, once you know this, now we need to introduce a tool to detect multiplicity. Okay, and now I am following ideas of MacLean. Okay. So, what is fixed point Floer homology? So I will not define the invariant. It was introduced by Dostoglu and Salomon. And the situation is the following. So consider M a Liouville domain, and let phi be an exact symplectomorphism of a Liouville domain. Okay, and compactly supported. So this means a symplectomorphism. Well, a bit more than symplectomorphism. So this means that phi upper star lambda minus lambda is the differential of some function that is called the axiom. Okay, and compactly supported means that is the identity in this color. Okay, so associated to it, you can define an invariant that is the fixed point Floer homology, and you can define it for M, but you can define for every iterate of M plus. Okay, so this is called fixed point. And the plus means, in order to define fixed point Floer homology, what you do is to perturb the symplectomorphism by a Hamiltonian. So you perturb phi to some Hamiltonian. You count the fixed points, and you create a complex that is generated by the fixed points, and the differential is created using pseudo-holomorphic curves. I will not enter into details, but it is important that there are no fixed points close to the origin. And then what you do is to use a Hamiltonian close to the origin that is growing. Well, actually, it depends on the convention. In our convention, it will be decreasing, and composing phi with a Hamiltonian diffeomorphism, then a small Hamiltonian diffeomorphism, you will make the boundary of the minor fiber rotate along rib orbits, and you take the Hamiltonian small enough so that the no rib orbit is completed. So in such a way, you obtain a symplectomorphism that only have fixed points at the interior, and you can compute the invariant. So you don't need to understand precisely what is the definition of the invariant, but you need to understand the following crucial property, that is that fixed point Floer homology is the formation invariant. Okay, what does this mean? This means that if you have a one-parameter family of compactly supported symplectomorphisms, exact compactly supported symplectomorphisms of a family of Liouville domains smoothly depending on F, then HF star of phi t to the power m plus is independent of t. This is a classical behavior in Floer homology. Very good. So now, once we have this invariant at our disposal, I would like to apply it to a mu constant family. Okay, so let's go back to the picture of a mu constant family. Okay, so now you would like so you are considering, so when you have a mu, I think I'll make this picture again, because in that part is a little bit dirty. So you have a mu constant family. You consider a Milnor ball. You consider a Milnor disk. And you consider the Milnor vibration. And now, let's consider the same ball epsilon 0. So from this point, I will never take the epsilon t ball. And now, the vibration that F0 defines on top of the disk of radius delta is isotopic to the vibration that Ft defines over the same radius because of the mu constant condition. The mu constant condition implies that there are no other critical values around. Okay, so if we could promote this result to symplectic geometry, then we would have some isotopy of symplectic monodromies, and then the fixed point Floer homology of them would be the same. So what is the problem if you try to define a symplectic monodromy? The problem is that you cannot guarantee that the area of this fiber coincides with the area of this fiber. But however, there is a trick to achieve this, and I will, in a very sketchy way, tell what the trick is. So I think, let's see if I can find some colors. No. Mm. Okay, so
To get colors, you have to click in the dots in the right hand side.
in the dots?
In the right. This.
Right, I see. Good. So you can do the following. You have in CN, you can put the standard symplectic form. Actually, this is the differential of the standard Liouville form, which is sum of xi dy. Okay, and now you can use the symplectic connection, and instead of using the Milnor ball, you start by this fiber and you integrate radially along the disk, and then you create a kind of cut like this. You create a kind of cut like this, and you do this also for the fiber at radius 0. And now, instead of considering the Milnor fibration defined with the ball, I'll consider the Milnor fibration cut by the symplectic connection. Okay, so we prove in our paper that it is possible to define a symplectic monodromy from this fiber to itself, and it satisfies the properties that I have mentioned above. So these properties, so what we create is, so from this picture, we create a family of symplectic monodromies. And therefore, to each function f, to each value of the parameter for all t, and for we can associate hf of phi t plus for any iteration, and this is independent of t. Okay. So all we have to do is to generalize the following, or to prove a modification of the following theorem of MacLean, and I will explain briefly what is the difference. So I'll say the statement of the theorem is the same for he and for us, but the monodromy that he considers is different than the monodromy that we consider. The theorem of MacLean is that the multiplicity of, actually, let me say, the theorem of MacLean is multiplicity of F0 is the minimal M, such that H F star F phi 0 to the power M plus is different from 0. Okay, so now let me explain why I have cheated you. If you have an isolated singularity, in differential topology, you can consider two fibrations. You can consider the Milnor fibration in the tube, and you can consider the Milnor fibration in the sphere. So MacLean theorem is for the Milnor fibration in the sphere, which is not known to be isotopic or to the Milnor fibration in the tube. Actually, MacLean theorem, yeah, so I think this is enough to say. And actually, even if you knew that the Milnor fiber in the sphere is the Milnor vibration in the sphere is isotopic to the Milnor vibration in the tube, for epsilon t, you need to consider the smaller radius, and the difference between the Milnor vibration would be given by this covariance that we don't know if it is symplectically trivial or not. Okay, so let me say what is our theorem. Is that the multiplicity of Ft is the minimal M such that HF star phi Tm plus is different from 0. Okay. And this phi T plus, I want to stress that is the monodromy defined for the bigger radius. So we do not use this. Okay. Well, immediate corollary is that mu constant implies multiplicity constant. Okay, so everything boils down to prove the following, to prove the, let's say, theorem A. So, how prove theorem A? So how much time do I have?
You have 15 minutes.
How much?
15.
15 minutes. Okay. So how to prove theorem A? So the main ingredient is a spectral sequence due to MacLean. So there are, well, two ingredients. And actually, this is a rather mild. And actually, and the tough part of the work is a construction, it's a deformation. Special dynamics. Okay, so let me say what is a monodromy with a special dynamics. And so this is really the part that differs from MacLean approach. Okay, so those of you that have seen the monodromy of a plane curve singularity will immediately understand what is the monodromy with a special dynamics. So let me picture, and I would like to stress that the proof of theorem A, so this proof is carried for individual E. So the family is going to be used only when we use the Le-Ramanujan argument. So I already use the family, or I have to use it. Okay, so let me picture this is the Milnor fibration. And now let me picture the Milnor fiber. So I'm going to picture a very long neck first that corresponds, let's say, to this coverdis. This is homologically trivial coverdis. And now the Milnor fiber will split in. So everyone knows the following model for the monodromy of a plane curve singularity. You make a resolution. You take the strict transform, that in this case could be very, very long. And now you make some boxes in the normal crossing. And you split the Milnor fiber into some covering of the exceptional divisors of certain degrees, and some interpolating pieces that are annuli. So the annuli that you see in the picture are interpolating pieces, and otherwise you have coverings. And now when you take phi to the power m, what in the coverings, what you take is the covering transformation to the power m, and interpolating pieces you have a kind of dent twist. Okay, so now a resolution of singularities is m separating. So you can write the exceptional divisor di. So these are the d1, d2, d3, and you have to put the strict transform too. So the strict transform will have m0 equal 1. And so the resolution is m separating if and only if when two divisors meet, then mi intersection mj, mi plus mj is bigger than m. And under this condition, it is easy to see that the only fixed points of the monodromy can be in the covering pieces. And actually, a covering piece will be a fixed point of the monodromy if and only if mi of, so now let me write it down. Oops. The di gives rise to fixed points if and only if mi divides. And in that case, the fixed points you see are the whole piece. So in particular, for every n, this long neck, the homologically trivial coverdis, will be a set of fixed points. Okay, so with this motivation, you can define monodromy with special dynamics. And it is for every m, the fixed point set of phi to the power m is a union, this union of bi, and the bi are domains in the Milnor fiber, zero codimensional domains whose boundary is a manifold with corners. And now there is an important property of this domain. So let's do one example. This could be such a domain. So such a domain will have a collar so such BI will have a tubular neighborhood MBI. So which is you put a collar for each element of the boundary in such a way phi to the power m restricted to NBI is Hamiltonian. So this means that there exists an H, and this Hamiltonian defines the monodromy. So you can assume that H is the identity on the fixed points, and it has to grow or decrease in the at the boundary. Okay, and accordingly to this, you can split the boundary of BI as boundary plus of BI, this union boundary minus of BI, and boundary plus are the components of the boundary where the Hamiltonian increases, boundary minus are the components where the Hamiltonian decreases. Okay. And now, MacLean spectral sequence, or the generalization. The generalization of MacLean spectral sequence is that the so let me say under special dynamics, sequence induced by the axion filtration. So if you don't know what is the axion filtration, please replace the phrase the spectral sequence induced by the axion filtration by there exists the spectral sequence has E1 page of the form. So the E1 will be sum of homology groups of BI boundary minus of BI. It's the relative homology group of BI boundary minus of BI. Very good. And I want to say only one property of this spectral sequence is that fixed I, all H star of BI boundary minus BI are in the same column. Okay, so this is what happens for arbitrary special dynamics. Now, I would like to say few more properties. Okay, so now I would like to say how do we deform. Actually, I don't have time to say how do we deform the monodromy to a monodromy with a special dynamics, but what I am going to do is to describe a little bit how the end result goes. Okay, you have these little boxes. And you have the tubes. And now you write the divisor as sum of mi di, and you remark that m0 has to be 1 because this multiplicity is 1. Okay, so now boundary of B0, which is B0 is precisely this piece of the Milnor fiber, is boundary minus of B0, which is the outer boundary is boundary minus, and the inner boundary is boundary plus. Now, if you notice that this covariance is homologically trivial, the contribution, so this means that the contribution of B0, boundary minus, of B0 is going to be 0, both for t equals 0, obviously because it is a Milnor ball, and for t different from 0, this is Bailey-Ramanujan. And the second property that you need to take into account is that the boundary of BIs, of all order BIs, you can compute that is always boundary plus. Okay, so this means that if a BI appears with I different from 0, then this contribution is non-trivial. Okay, so now let me show how to prove theorem A. So we do the following resolution. So we start by the function, and now the first blow up that we consider is the blow up at the origin. So this will create some exceptional divisor with multiplicity M1 equal multiplicity of Ft. And now you do Hironaka process, and then you continue blowing up. Until you reach an M-separating resolution. And in fact, all the MIs will be bigger than the multiplicity, except the strict transform 1 that will have M0 equal 1. Okay, so now if you compute Floer homology for phi to the power m plus, if m is smaller than the multiplicity, if m is smaller than the multiplicity of ft, the only contribution is the 0, 1, but we said that the 0, 1 does not contribute because of Le-Ramanujan. Okay, if m is exactly the multiplicity, the only mi that can divide m is precisely m1. There is only one contribution that does not vanish and is in the same column of the spectral sequence. So this means that the spectral sequence degenerates and the Floer homology is different from 0. And this would end the proof of theorem A. So I think I have 1 minute at least, no?
Yes, 1 minute.
Yeah. So let me use the minute to say how do we prove, so what are the steps? Okay, so the steps are the following. First, resolution of singularities. And now you have a divisor. You consider the log scheme, and you do the Kato-Nakayama construction, which is the real-oriented blow-up. And on top of this, you do a further blow-up that interpolates pieces of the dual complex, and you create a space that is the very same space that Acampo constructed, that is the Acampo space. So you need to endow with a C infinity structure and with a symplectic form. And it is such that the Acampo space fibers. So these fibers over C log Okay, and C log is nothing else than an annulus, and it has a radius 0 cycle. Okay, and now in the outer circle, you find the usual monodromy that we defined, and in the inner cycle, if you lift the symplectic connection for this symplectic form, the special dynamics appear, and all the process of forming the usual monodromy to the special dynamics monodromy is a radius reduction. And I cannot say more in the time I have, so let me stop here.
Are there any questions? Okay, if there are no questions, let's thank the speaker again. Thank you very much, Javier.
Okay, well, thanks, goodbye.
Muchas gracias, Javier. Un abrazo.
Me alegro de oírte, Pepe.
Adiós.
Adiós.